Hello everyone and welcome to this talk on design patterns. Now, in this first video, I want to introduce the concept of design patterns, see what they are and what they are useful for, and also why you might want to use them in your coding and in your application or project. So what are design patterns? Design patterns are basically ways of solving similar problems in similar ways. Okay, so during our development, pretty much no matter what language you develop on, you will run into kind of the same issues and you might want to implement the same solutions. Okay, so design patterns gives us a way of fixing or solving a problem in a kind of accepted standard way. We know that these solutions work and we want to use them to implement them in our code. So design patterns will allow us to do that. They will allow us to have the certainty to know that our solution does solve the problem, but also introduces some other things that we might want in addition to simply having a solution, whatever that solution may be. So these things might be scalability, where your application or code might be able to grow when you add further functionality and further code to it. So scalability is one thing, testability is another. We want our application or project to be tested in a simple way, and we can introduce unit tests and more complex tests. Okay, so design patterns allow us to do that. It also introduces separation of concerns. Okay, so that means our code is split into kind of blocks of code or components that each solve their individual problems. And this in turn leads to better architecture and better, scalability, maintainability, things like that. So that is at the core, that is what design patterns are. In addition to all that, they introduce standard terminology. Okay, so we want to be able to discuss the solutions to our problems in an easy way. And speaking to, let's say, developers or architects about your code, about your project, using design patterns provides an easy way to kind of communicate what you have done. So for example, if you say that you have implemented a builder pattern for a particular class, then the person you're talking to will automatically know what you are talking about. They introduce best practices, so that means what are the most efficient ways, the best ways to solve certain problems in your code. In software development, we often have one right way to to solve a particular problem and many kind of wrong ways. Even though the solution might work, you might not get things like separation of concerns if you, let's say, put everything in one code, right? So that would be an example of a wrong way to solve a problem. Design patterns introduce best practices, the best way that we have found to solve particular problems. Now, I want to introduce this term. You might have heard of it, the Gang of Four. The Gang of Four is basically a group of four software development architects that have put together the book, the foundational book on design patterns. Okay, and this is what this course is kind of based upon. They describe, based on their experience, they describe the best ways to solve a lot of problems and come up with some solutions to common problems. Okay, they have named these solutions design patterns. They provide a number of them that we will cover here in this course. Okay, so this is what it's based on. There is a book out by the Gang of Four, so if you want more information, check out that book as well. All right, so that's it for this introductory video. Thank you for watching. I will see you in the next one. All right, so the types of design patterns. Now, of course, we have different types of design patterns depending on what we want to achieve with a particular pattern. Okay, so in this video, we're going to go through the three types that we will cover in this course. The first one is going to be the creational type of design patterns. And the creational design patterns basically relate to how you create specific objects or specific components in your applications. Okay, so why do we have this? Well, we have different ways of creating objects or components depending on the requirements we put on those. So you can imagine, for instance, a class that has multiple parameters. We want to, let's say, instantiate some parameters and not others. And we want to do this in an efficient way to provide the quote-unquote user, so the caller object, with a lot of options and a lot of possibilities. And this is where, for example, the builder pattern would come in. Okay, so different ways of creating objects or creating components in a way that achieves the nice-to-haves that we talked about. The second type of design patterns is the structural. And here we talk more about how we kind of structure our whole project, how we structure our application, to achieve certain objectives. This is sort of related to architecture, although architecture is kind of a broader view which relates to components and which components are responsible for which actions. Here in the structural design patterns, we take a kind of closer view, closer to the individual class or component, and see how that component is structured in order to, again, achieve some nice-to-haves, like testability, scalability, and so on. And the final type of design pattern is going to be the behavioral. And the behavioral pattern relate to how the components that we create behave in our application and interact with each other. Okay, so here is where we will see how we communicate between components based, again, on the structural types of design patterns. Here we see how those components that we have created kind of interact and communicate with each other. And here we will have quite a number of design patterns that we need to go through, but all are quite useful to know, and I think you will use most in your development and in your projects. Okay, so this is kind of a broad view of what types of design patterns we have, and in this course we have split the structure of the course. We have sections for each individual type. Okay, so firstly, we will talk about all the creational patterns, and we will begin that in the next section. Okay, so thank you for watching this video, and I will see you there. Okay, so let's get into it. The first design pattern we're going to talk about is the singleton. Now, if you've heard of one design pattern, this is probably the one you heard about. The singleton is probably the most well-known and the most talked about design pattern, both in a positive way and in a negative way. It's not necessarily the most used one or the most useful, but just that people do talk about and know about the singleton. And we're going to cover the positives and negatives in this video. So let's take kind of a thought experiment to understand why the singleton might be useful. So let's say we have a project with 3 components, and these 3 components need to access some external resource, for example, an API on a network on the internet. So a naive solution to this would be to have a network communicator. We instantiate that network communicator every time we need to access that resource. So for example, for component 1, we have its own instance. Component 2 has its own instance as well. And we communicate with the resource in this way. Now, there are a few problems with this. So first of all, this is kind of resource inefficient. So you might be on a smaller device that doesn't have enough resources, or you might be on a server where you have a lot of access and you want to conserve your resources. In this case, creating 3 instances that do the same thing, that is not a very efficient solution. Also, you might want to have some sorting, some ordering of requests in this communication. Okay, so you might want to serve each request as it comes in and order those requests if that is important. Okay. Also, for testing purposes, this is not very efficient because you cannot you shouldn't really test multiple instances of the same thing. So a better solution would be to have a singleton, which is going to be a single instance of this network communicator. And then all the components that require that functionality will access that network communicator. Okay, so this is kind of the idea behind the singleton. put a central resource in a single instance of that resource rather than duplicating it multiple times. Okay, so only one instance. It's a single point of access for a resource. And we've taken the example of a network communicator, but we might have, for example, a database or a logging system or things like that where you want a single resource. Okay, so here are a few examples, but of course, it's not limited to that. Now, as I mentioned, there are some disadvantages to singletons, and people are often quite against this pattern. The main ideas, the main reasons why people don't like them are, first of all, it breaks the single responsibility principle, which means that a singleton will basically manage its own state and will allow others to create only one instance. And this is not ideal. This is often a code smells, quote unquote code smell, which simply means that a particular class should create a component when required, whereas the singleton creates its own instance. Okay, so this is not ideal. Also, testability issues might come in since the singleton kind of handles multiple situations, multiple cases, multiple components will access that singleton. By its very nature, where you have a single instance of a component, that means you couple tightly the components that need the singleton with the singleton instance. Okay, so this kind of reduces testability. You cannot really mock a singleton in a test since you have only one instance, and you need to, kind of get around that in some way. Also, you have a state for the lifetime of your application. Okay, so once the singleton has been instantiated, you can only use that particular instance. Of course, you could implement a solution where you kind of kill that instance in some situations and recreate it, but that would break the principle behind the singleton. Okay, so that means once a singleton is instantiated, you have your state for the lifetime of your application, and that causes some issues. All right, so enough with the theoretical introduction. Let's go to our editor and start to implement a singleton in our code. Now here I am using PyCharm for development, but you can use any editor you like. And I've just simply created a new project here. Okay, so let me just delete that file. All right, now we're going to, let me just create a Python file. We're going to implement the singleton in two different ways. The first way is going to be a naive implementation where we implement a singleton that works, but I will show you a particular case where it doesn't work. To kind of tell you straight away what the issue is, it works in a single thread, but not in a multi-threaded environment. Okay, so we're going to implement this naive implementation, and then we're going to see what the solution is and how we can fix the multi-threaded implementation. Okay, so first of all, I'm going to have a naive singleton. So let's implement this naive singleton. I'm going to have a class with a singleton, and I'm going to have a type here. Okay, I'm going to have underscore instances is going to be this empty dictionary, and I'm going to override the call method. So def underscore underscore call. And I have here self args and kw args. Now, I'm going to say if self not in self dot underscore instances. So if we don't have that instance, then we will create it. So instance equals super dot call. Okay, here we have args and kw args. Okay, and then we're going to have self dot underscore instances of self equals instance. Okay, and outside my if, I'm going to say return self dot instances of self. So what I'm doing here is I'm checking, does this instance exist? And if it doesn't, then I create it. and I add it to my dictionary. If it does exist, then I don't need to create it again, and I simply return it. Okay, so that will just create a single instance for my Singleton class. Okay, I'm going to have here a class network driver with a meta class Singleton. Okay, and here I will just have a method define log of self, and I'm going to print an F string, and I'm going to have self, and I want a /n at the end. That should be, I've put self here twice. There we go. So I will just define a method that prints out my instance of my class. Okay. And then finally, I will have a def create Singleton. Okay, no parameters here. And I want to have Singleton equals network driver, singleton.log, and I will return Singleton. Okay, so that is my creation function. So here I will have a main, and I will say, let me just put a comment here, single thread. Okay, so we're on a single thread. I'm going to say S1 equals create Singleton, and S2 equals create Singleton. Okay, so I create two singletons, but obviously if this works as it should, then only one singleton will be created. Okay, so let me go ahead and run this, the quote-unquote naive singleton, and we can see here that the created objects are exactly the same. Now, the problem comes when we implement a multi-threaded environment. I've just realized that the text is quite small, so let me just update this. Let me search for font size 16. Let's put it to 20. Hopefully, what is happening? Okay, so hopefully that is easier to see. Now, so as I mentioned, this is a single thread. So let's add a here multi-thread. All right, so for multi-thread, we're going to say process P1 for process 1 equals, I need a thread, of course. So let me just go at the top here, and I'm going to say from threading import thread. Okay, so I have my thread. Let me put a space here. Okay, going down, I have P1 equals thread, and I have target equals create singleton. Okay, and I will have P2 equals thread with target equals create singleton. So this will create two singletons on two threads. So let's see how this works. If I run this, okay, so I need to comment out the creation, because the creation, once the creation is done, of course, the singleton is created. So we will get the same thing. And I'm thinking, because this creation here can happen really quickly, I would need a bit of slowdown. So in a real world situation, this might be delayed to, instantiate some resource. So I want to simulate that. I'm going to put here import time. If I type this correctly, import time. And I want to simulate here that this might take, let's say, time.sleep for 1 second. So it will take, let's say, 1 second to create this singleton. And in this case, that will cause some issues. Okay. The reason I've done this here is because in a real world situation, it takes some time to instantiate some resources on your machine. So for example, instantiating a connection to a database or to a network communicator or whatever it is. Okay, so with that, let's run our naive singleton, and I've just forgotten here to say p1.start and p2.start. Okay, so running that again. This should not be a function call. All right, we got there in the end. Okay, so sorry about that. There was a bit of confusion, but in the end, we basically create two threads. We start them, and as we can see here, we create two different objects of this class, right? Here we have 40, here we have D0. So these are two different instances of our supposedly single instance class. Okay, so that is a problem in a multi-threaded environment. So how do we actually fix this? Let's go ahead and create a new Python file. Here we have, let's say, thread safe singleton. Okay, I'm just going to copy everything from here and paste it here. The way we solve this is once we start to create our singleton, we need to have a lock so that we lock the thread so that other threads cannot access it here. Okay, so in order to do that, I'm going to add lock here from threading. And in my singleton class, I'm going to have underscore lock is going to be lock. All right, so I have my lock. And in my call function, I'm going to say with, here I have self.lock. Okay, and I'm going to put my if inside this with block. Okay, so with that done, I think the rest should stay the same. And I'm going to just run this. And you can see that we have the same instance for both threads. So what is happening here is basically whenever we enter this function call, we lock the thread to check whether or not there's an instance. Okay, so that is all that we need to do. Once we have that determined, then we can simply return the instance that is available. So that is how you would implement the singleton for multi-threaded environments. All right, so in this video, we're going to talk about the factory method. Now, here is the problem that this design pattern will try to solve. So first of all, in our development, in our projects, oftentimes requirements change, and we do need to go into the code and change some particular aspects depending on what new functionality is needed, or we need to refactor the code that we have to adapt to new changes. Okay, so this is where factory method will come in because it will cause kind of a separation between the creator of an object and the user of that object, right? So that means this separation will allow us to change our code more easily without impacting a lot of our code. Now, dynamic switching is also a quite interesting topic because in a real life situation, you might have, for example, you might have multiple data sources or you might have multiple databases, and you want to be able to switch between those databases in a dynamic way based on certain requirements in that particular moment. Okay, so we don't want to have a tight coupling between the user of the object and the creator of the object so that we can change that object dynamically based on other requirements. Also, there is the principle of separation of concerns, which means that you want to separate the creation from the utilization. Okay, this is kind of a general principle in software development. So how does factory method help with all of this? First of all, the design logic and the creation or instantiation of an object is hidden from the client. So the client doesn't really know how to create the object. It just knows how to use it. So that means multiple classes of objects will be able to be created, and the client will have access to it without knowing which exact type it is actually using. We have many subclass types, but only one instance, right? So as I mentioned, we can have multiple classes, multiple types of objects, but as long as the utilization or the interface is the same, then we only need one instance and we don't really care which instance, which type it is. Creation is removed from the client. Obviously, we need another object that creates objects or another class that creates objects. And then this is useful for frequent code changes. So when we want to update our code, when we want to introduce another type of this object or this component, this is where the factory method really shines, because the separation is done in a way that we can just add or subtract multiple types and the code will still work seamlessly without impacting too much. So to kind of give you an overview how this will work is here we have, for example, 3 types of databases, okay? We have instances of these databases. These connect to their respective databases and use their particular language. However, all of these objects that access the database will have the same interface. So that means this interface will allow us to communicate with either one of these without really caring about which particular instance we are dealing with. And then we have the database factory. In this example, this is a generic factory that creates the particular instance that at that particular time is required. Okay, so this is where the separation kind of comes in. The client doesn't really know or doesn't really particularly care which instance it is using, as long as it gets an instance with this particular interface. So you see the separation here between utilization and creation. So the components that are required basically will be an interface or an abstract class that defines the common functionality, the implementations, one or more, as many as we need, and we can add, as the project kind of grows and matures, we can add more implementations based on that particular interface, and then the factory class that instantiates the right implementation for that particular use case, for that particular situation. All right, so that is all for the theoretical introduction. Let's move to our code, and I'm going to create a new file here, new Python file, and I'm going to call this factory_method. All right, so in the factory method, we're going to add, first of all, we're going to add some objects to kind of serve as the things that we kind of move around and pass around in our code. So here I'm going to have a class country. And what I would like to do, I'm going to just pass here. What I would like to do with this code is I would like to have a kind of quote unquote currency factory that will give us the currency for that particular country. Okay, and we will have multiple instances of those currencies. We will see how that works. So I have my class country, and I will have another class here, let's say USA, that is a subtype of country. I'm going to pass here. I will have class, let's say Spain, country, pass, and let's add one more, class Japan, which is also a country. All right, now let's create a kind of abstract class. However, since Python doesn't natively support that, we need to import from ABC, import ABC and abstract method so that we can create abstract methods. And down here, we will say class currency factory. Okay, this is going to inherit from ABC, and we're going to have an abstract method. Let's define currency underscore factory. Okay, we have ourself, but we need to pass the country here, and we will return a string. And for now, we're going to pass. Okay, so this is the abstract method, which will allow us to implement our factory. Okay, so we have our currency factory. Now let's define, this is our interface. Let's define our, let's say, fiat, which is the usual kind of money that you have in a country, the usual currency, fiat currency factory. And this is going to be a currency factory. Okay, so we're going to define here our currency factory. that returns a string, and we're going to say if country is USA, then return USD, United States dollar, elif country is Spain, then return euros, else, I forgot, there we go, else return JPY, Japanese yen. Okay, so very simple, very standard. Now let's create another one that's going to be virtual currency factory. And this is also going to be a currency factory. Let me just copy and paste this because it's going to be exactly the same. However, here, instead of USD, let's return, let's say, Bitcoin. For Spain, let's return Ethereum. And for Japan, obviously, we're going to return Dogecoin. Okay, so we have our factory. So now we can simply have a client code. So let's implement our main. We're going to have F1 equals fiat currency factory. And F2 is going to be virtual currency factory. Okay, so now if we use F1, we're going to say print F1 dot currency factory, and we're going to do that for USA, and that's going to create the USD. And let me just duplicate that 2 times. And instead of USA, I'm going to have Spain, and I'm going to have Japan here. Okay, so this is all with F1, and I'm going to copy and paste, and I'm going to replace this with F2. Okay, so this should generate all the coins, all the currency that we have in our application. There we go. So USD, Euros, Japan, and then Japanese yen, and then we have Bitcoin, Ethereum, and Dogecoin. All right, so that is the implementation for the factory method. So you can see the use is where we use in our code, in our main code, is separated from the creation, right? We don't know how to instantiate these currencies, but the factory itself does. So that is really useful in a lot of situations in your project. Abstract factory is, you can think of it as kind of one level of abstraction above the factory method. And it is simply put, it is a factory that creates factories. Okay, so just one level up. So let's see how this works in practice. So let's imagine we have a data source here, data source type. This is an interface. And then we have database, we have user input, network, and whatever other data sources we might want, we might have. All of these have underneath them, they have certain types. So for example, the database might have SQL database, MySQL database, or whatever type of database. So you can think of this as kind of a factory for databases, factory for user inputs, and so on. Now, which one we use doesn't really matter from the point of view of the user, which is in our case is going to be the display. So the display doesn't really care where it gets the data as long as data is retrieved in the way that it wants. So in this case, we can have a data source factory, which is kind of higher level abstraction, which gives us the data source, whatever that data source may be. Okay, so the data source factory instantiates the actual factory that we're going to use, which in turn will allow us to access the resource. Okay, so this is how it works. We have a data source factory here. We instantiate the particular database factory, network factory, or whatever we will need. And then that in turn will implement the data source. Okay, and I haven't drawn here, but obviously the database and network will retrieve the actual information. So Abstract Factory provides a way to access functionality without caring about implementation. This is kind of true for the factory method as well, but as I mentioned, this is a one level up, And in this case, we don't even care about which factory we use. Okay, so we want to abstract that information away as well. One level of abstraction higher. And again, it follows the principle of separation of concerns. Okay, so we don't care about how we don't care about how we create the object. We only care about using that implementation. And again, here it allows for testability. So we separate the concerns, we separate the components in our application, and therefore we can more easily test components in isolation. Okay, so that is the theoretical introduction. Let's move to code. And here we are in our editor. I am in PyCharm, but you can use whatever you like, obviously. I'm going to create a abstract factory file. First of all, like in the factory method, I'm going to say from ABC import ABC and abstract method. Okay, so that we can create abstract classes. Now, what I would like to do here is I would like to have kind of a practical example, and we're going to implement a quote-unquote restaurant factory. Okay, so we want to have a particular type of food. As a client, as a user, I want to decide what kind of food I want, and then I would like to go to a restaurant. So I don't really care which restaurant it is. Obviously, in a real world situation, you might care for other reasons, but in our situation here, we don't care what restaurant as long as we get the type of food that we want. So the abstract factory is going to be kind of the restaurant creator. The factory implementation, we're going to have a, let's say, American and French restaurants, and the client, the user, is going to just care about the food that it receives. Okay, so let's implement that. We're going to have a class food type, and we're going to have French equals 1, and then American equals 2. Okay, so we have our food type. Now let's create an abstract factory. Let me put here an abstract factory here, and I'm going to have class restaurant. And this is going to be ABC. And the restaurant is going to have an abstract method. Let's say define make food. And this is just going to have self. We're going to pass for now, and let's define another method, abstract method, define make drink. Okay, and we're going to pass for now. All right, so let's define a class restaurant that inherits from ABC. We're going to have an abstract method. Let's say define make food. Okay, we're going to pass for now, and another abstract method, define make drink. Okay, and we're going to pass. All right, so we have our restaurant kind of interface, and here we're going to create a first type of restaurant that's going to be French restaurant, which obviously will inherit from restaurant. So here we need to define make food, and we're going to just print some food that we make. Let's say cordon bleu. Okay. And then we're going to define make drink, and we're going to print something like Merlot. Okay, so that is our French restaurant. We're going to also define a American restaurant. Okay, so these are all factories, right? So restaurant, and we're going to have our make food. Here we're going to print hamburger and define make drink, and we're going to print something like Coca-Cola. Okay, typical American food. Right, so now we want to have our abstract factory. So let's define a restaurant factory. Okay, so the client, the user, doesn't really care which type of restaurant they care which type, but they don't really care which instance of the restaurant, right? So that's what the restaurant factory will create. So here we will have a def, let's say, suggest restaurant. Based on here we will have a type, which is going to be food type. I think type overrides some built-in type. So let's say R type, restaurant type. Okay, so we have our R type. And now we can say if R type equals food type dot French, then return French restaurant, else return American restaurant. Okay, so we have our restaurant factory. Now we just need a client method, def dine at, and here we have our restaurant of type restaurant, right? So this is going to simply print line. Let's say for dinner, we are having, I forgot to put the quotes, right? So for dinner we are having, then we will simply call the method in the restaurant. So make food and restaurant dot make drink. Okay, so that is the client method, and we of course need a main. Here we have, let's say, suggestion. Suggestion 1 is going to be restaurant factory dot suggest restaurant. And let's say first we want some French food, so food type dot French. And then for suggestion 2 is going to be restaurant factory dot suggest restaurant food type dot American. Okay, so the first suggestion is going to print our French food and drink. The second one, American food and drink. So we're going to dine at the first suggestion and then dine at suggestion 2. Okay, so pretty self-explanatory. I think the abstract factory, the restaurant factory, will basically create the factories that we have, French and American, and these in turn will share a common interface, which we have defined here as restaurant. So we can actually use them in the client without really caring which type there are, which instance they are. We know the food that we want, and based on that, the factory method, the abstract factory, defines our restaurant, but we don't really care about the instance. Okay, so here is where we use it, and we just call that in dine at. So let's run this. The only thing I forgot here is to make this method static. It's also a suggestion there. So we could just create a instance here, but this should be easier, right? So this is static. For some reason, the types have disappeared. So food type dot French and food type dot American, right? So since this is a static method, we can now access it. So let's go ahead and run this. There we go. So it is working as expected. For dinner, we are having French food and then American food. All right, that is all for the abstract factory design pattern. All right, in this video, we're going to talk about the builder pattern. Now, the builder pattern is really useful in many situations because it allows us to have an object that is initialized in different ways. So you can think about an object that has multiple parameters that we need to initialize. And in some situations, we might want to use some parameters. In others, we might want to use another set of parameters, right? So the builder allows us to be flexible when initializing an object. For example, if we have many parameters, it's quite impractical to build all constructors, to build the object that has the multitude of options when it comes to building it. So for example, if we have 5 parameter combinations, that will give us 120 constructors. So we don't want to list kind of all possible permutations and combinations of these parameters. We have some optional parameters in our objects, which means that some parameters are mandatory. Others are optional, so we might exclude them if we want to when building our object. And in addition, it should be quite easy to read. Okay, so we should have a way to construct the object that is easy to understand and easy to use by whoever wants to instantiate that particular object. All right, so that is all for the quick introduction. Now we're going to move to our code. And we're actually going to see two ways of putting in place this builder pattern in Python. One is the classical way, and one is kind of a simplified way to achieve the same thing in an easier way. All right, so let's start with the first one. I'm going to create a new file, and I'm going to call this builder. So what I'm going to do here is I'm going to have a class called network service where I can instantiate it with different parameters. We're just going to have 3 parameters in our example, but you can add many more if you like. So you can kind of visualize how that would be. So let's have a class network service. And we're going to define our init method here. And we're just going to say self.components is going to be an empty dictionary. All right, so we're going to add a key of type string and a value of also type string. And we're just going to say self.components of key is going to be value. Okay, easy enough. And we also want to just print out our components to see what we have there. So here we have .show. Okay, and I'm going to say print self.components. Okay, so that is our network service. It's quite simple, but as you can see, we can add as many parameters as we like here. Now, for the purposes of this design pattern, we're going to have a class network service builder, which we're actually going to use to instantiate our network service. So here I'm going to define an init method, self._service is going to be a network service. All right, now let's add a few things. So first of all, we might want to add a target URL to our network service, right? So def add target URL. And here we have our URL of type string. So what this does is basically it says self._service.add, and we have a key URL and our value URL. Okay, easy enough. That's the target URL. Let's define a couple more. Let's say add auth. Okay, so that's authorization. And here we have self and auth of type string. Okay, we're going to say self-service.add. We're going to have the key authorization. And we're going to have the value auth. Okay, and finally, we're going to add something like cache. Add cache, or rather caching, because this is just the time interval for the cache. Okay, so caching, and here we're going to have our cache of type int. Okay, and we're going to say self._service.add. Here we're going to have cache control, which is how you would spell that in the URL headers. Okay, and here we have our cache. Okay, that's going to be converted to a string automatically. Now, we're going to define also a method build that will return us a network service. Okay, so we're going to simply say here, service equals self._service. I want to reset this _service. So _service equals network service, so reinstantiate that, and then I'm going to just return our service. Okay, that is fine. So here we have our builder, and now we're going to use it in our main. So let me define the main, and we're going to just say here builder equals network service builder. And now we can use it to create our network service. So first of all, we will create a very simple network service that doesn't have authorization and doesn't have caching. So we're going to say builder.add target URL. That's the only thing we're going to need. And let's say google.com. Okay, so we have our first network service. We're going to say service1 equals builder.build. And then service1.show. Okay, so we're just going to print it out. Now, this has been reset. Okay, so we have it here. We reset it. So we're going to create a new one. We're going to say builder.add target URL. Let's say youtube.com. We're going to say builder.add auth. Okay, so here we have, let's say ABC123. This is the key for the authorization. And finally, we're going to add caching. And let's say this is 60,000 milliseconds. That's 1 minute. And then if we do service2 equals builder.build and then service2.show. Okay, so that should basically build our two services. So let's go ahead and run this. And we will get the first one. We have only the parameter that we have instantiated. And the second one, we have all three parameters. Okay, so very, very clear, I would say, how we use this builder to instantiate the network service. Now, as I mentioned earlier, we have actually a simpler way to do kind of the same thing. So this is the classic way you would build a builder, okay, if you require some more complex functionality. But let's keep it simple and let's create a new file, builder2. And in this file, we're going to build the same thing, except we're going to take advantage of the named parameters that we have in Python. Okay, so we're going to have class network service. Okay, and here we're going to have our init function. But here, the difference is we're going to pass all parameters here in the init function, and we're going to give them default values. So URL of type string and empty by default, empty string. We're going to have auth of type string, also empty by default, and we're going to have cache of type int, and that is going to be 0 by default. So here we're going to build our dictionary. So self.components is going to be an empty dictionary. Now we're going to say if URL. Okay, so if this is not empty, then we're going to just add it to our components. So self.components of URL is going to be our URL. And we're going to do the same thing for the other. So if auth self.components of auth, this is authorization, is going to be equals to auth. And then if cache, so if this is not 0 because this is an integer, we're going to say self.components of cache control is going to be our cache. Okay, very, very simple. So this is kind of equivalent to what we had previously. And now let's define our show function. And here we're just going to, like before, we're just going to print self.components. All right, so we have that. And now that is basically all we need. Okay, so this is equivalent to these two classes. So now we can use our main. And we can say here service1 is going to be equal to network service. And here we have the option to provide the names of the parameters. So we're going to have URL google.com, and we're going to leave it at that and say service1.show. Okay, and service2 is going to be network service, and we're going to provide more parameters this time. So we're going to say URL equals youtube.com. We're going to say auth equals ABC123 and cache equals, what did we say here? 60,000. Okay, and service2.show. So that is basically all we need. This is equivalent to all of this, right? So let's go ahead and run this code. And then we get the correct output, what we were expecting. So that is the builder pattern. It is quite useful, especially the second version that I've shown you here. It is quite useful and quite often used to provide optional parameters in your initialization. Okay, so you will find it quite often in code. All right, the last of the creational patterns that we're going to talk about is the prototype. Now, here is the problem that this is trying to solve. So let's say in our code, we have some existing object. It can be of pretty much any complexity. And for some reason, we need a copy of that object. Okay, so we don't want to kind of create a new object from scratch and then go through the whole process, because this particular object might already have some state in it or has gone through user interaction or some other reason, right? So there is some complexity in this existing object, and we just need a simple copy of that object. How do we do that? Well, the problem here is that we cannot simply copy the existing object, because some fields for example, might not be visible in that object, right? So we cannot go and kind of get each field individually and initialize a field with the same name in the new object. We cannot go one by one. Also, we might only have an interface to that object. We might not have the reference, the object itself, right? So we might not know exactly what we're dealing with. Also, a kind of a third problem in copying line by line or field by field is it requires tight coupling, in the sense that we would have to know exactly the structure of that class of the initial object that we're trying to copy. Okay, so that's obviously going to lead to tight coupling, which is not ideal. So what does this prototype need to do? First of all, it lets us copy existing objects. Okay, quite simple. We will not be depending on their class. That is quite necessary. We can have situations where we only rely on an interface. The copied object must provide the copy functionality. So we don't want to externalize this functionality outside the existing object. We want the object itself to provide the copy functionality, because the object itself will have access to everything that it needs. And it avoids tight coupling on the outside. Okay, so it will have access to its private fields. It will have access to all the required functionality, to its state, and so on. And then finally, this is quite useful in testing and pre-production. So for example, you might have a live system where you have certain long-lived objects like a database connectivity or some user state management object, something like that. If you want to test that object, or you want to kind of provide some pre-production staging environment, then you want to be able to copy those objects into your second system. Okay, so quite useful. All right, so that is the kind of theoretical overview. Let's go to our code. Now, the good news is that Python out of the box provides us with this copy functionality. We just need to kind of import it in our project and know how to use it. So let's go ahead and create a new file here. And I'm going to call this prototype. Okay, now the copy functionality is going to be in a copy package. So we're going to import copy. Okay, and I'm also going to import, from ABC, import ABC and abstract method, so that we can define kind of abstract functionality. So what we're going to do here is we're going to have kind of a theoretical example. We're going to have a shape structure. These are the objects that we're going to have in our code, and we're going to, using these shapes, we're going to build a quote-unquote abstract art functionality. Okay, so an object that combines these shapes together to provide some output, and we want to copy this art. Okay, so we're going to have here class shape that inherits from ABC, and we're going to have an abstract method def draw, and we're going to pass for now. Okay, so with this shape, we're going to have a class square. That is a shape. And we're going to define the init function here with a size parameter. So we're going to say self.size equals size. And obviously, we need to define the draw method that simply prints out a f-string drawing a square of size and the size that we have, self.size. Okay, so that is our square. Let's define one more. We're going to have a circle here, which is also a shape, very similar in it. We're going to add a parameter radius, and we're going to say self.radius equals radius, and def draw, print a f-string drawing a circle of radius self.radius. All right, so very good so far. Now, we're going to have an object that we will eventually copy, and that's going to be class abstract art. Okay, here we're going to have an init. We're going to override the init, and we're going to say, let's say we have a background color, and we're going to have our shapes. So self.bg color equals bg color, and self.shapes equals shapes. So shapes is going to be a list. So we're going to say def draw. Okay, and we're going to just print a f-string background color is self.bg color, and we're going to print all these shapes. So I have x.draw for x in shapes. X.draw a function call here. All right, so we have our abstract art, and we need to just have a main where we can create some objects. So here, let's create some shapes. That is going to be a list. Let's say we have a square of 5. We have another square of 3. And we have a circle of 8, for example. And then we can create an art1 object that is going to be an abstract art, where we provide the background color as red and provide these shapes. Okay, so far so good. Now, this is quite basic, quite simple functionality. The prototype part comes just now with this copy functionality. So as I mentioned, we get this by default out of the box. So we can say art2 equals copy.copy. We have two options here. We have copy and deep copy. The only difference is that with copy, the objects that you have inside your copied object will be copied by reference, whereas the deep copy will copy the objects themselves as well. So copy just gives you references. Deep copy gives you copies. Okay, so I'm just going to use copy. In our example, the output is the same. The result is the same whether we use copy or deep copy. So here we have .copy of art1, and we're going to have art1.draw and art2.draw. Okay, so we're just going to print them out just to see that they are exactly the same. So running that, we get the art1 and art2. Okay, so they are exactly the same. They have the same parameters, and the kind of prototype pattern was implemented automatically for us, was given to us out of the box with the copy package. All right, so the first of the structural design patterns that we're going to talk about is the adapter. And the adapter is kind of maybe the easiest to understand of the patterns. What it does is simply it converts one interface of one class into another interface that the client expects. What this means is that we might have in our code, we might use a third-party library, or we might have some part of our code that is used in multiple places. So that means we cannot actually modify that particular class or that particular interface. So what we want to do is we need to convert the interface that we do have control over, and we want to be able to access the third-party library or third-party interface in an easy way. So we cannot contact it, we cannot access it directly because these two interfaces are more or less incompatible. So what we do need is some sort of adapter between our interface and the third-party interface. Or we can think of it as converting data from one format into another. Whether we're talking about interfaces or data, we still need this kind of adapter between the two types. So here is a small diagram to kind of show you in graphic form what we mean. We have a client that has a target API or target interface, and we need to call this adaptee interface that we cannot modify, have no control over. So what we do is we implement this adapter class that converts the call that we have in our code to this specific call in the third-party library. We don't want to put this functionality, this adapter functionality in our target because we want this kind of separation of concerns. And also we might not want to modify the target if it's used in multiple places in our code. So the best solution is to have this separate adapter class that converts from one type to another or converts the data from one type to another. All right, so let's move to our code and let's go ahead and create a new file here. And I'm going to call this adapter. So what we're going to do here is we're going to have a type of data in the third-party library. We're going to implement that and kind of think of it as immutable. We don't have access to it. And we're going to then implement this adapter class that converts from one data type to another. So first things first, let's go ahead and import from data classes, import data class. And let's define here a data class. And I'm going to call this class display data type. Okay. And this will just have an index of type float, and it will have some data of type string. Okay, so I'm going to mark this as third-party functionality. Okay, we don't have access to it. We cannot modify this functionality. Also, in the third-party functionality, we have a display data class. Okay, and this has an init where we have some display data of type display data type. And we just want to store it for now. So we're going to say self.displayData equals display data. And we have some functionality. So let's say def show data. Okay. And we're going to just print line an F string, third party functionality. Okay, we're going to have here self.displayData.index. We're going to put some dash line and then self.displayData.data. Okay, so we just want to show the data in a certain way, and we're going to assume that this is kind of third-party functionality. It's a bit more complex, but we're going to simplify it here just for the purposes of this code. All right, so what do we do with this data type? We cannot simply use it. Let's say we want to store it in some database. This is display data, so we cannot just simply access it as it is. And here we're going to implement some of our own functionality, so our code. Okay, this is part of our functionality. Let's say we define a data class. class database data type. Okay, and this has a position of type int, and it also has a, let's say, amount of type int. All right, so we have our code. Now here we also have a class store database data. Okay, we're going to define an init function. Okay, here we have database data of type database data type, self.database data equals database data. And we're going to have some local functionality, some of our own code functionality. Let's say store underscore data. Okay, we pass some data here and we'll just print it out. So print an f string database data stored, and let's just display the data. So self.database data position, some dash line, and then self.database data amount. All right, so this is our functionality. So what we want to do is we want to access this show data, but we don't want to do it directly for the reasons that we mentioned previously. So what we're going to do here, we're going to create a class display data adapter. Okay, and in this display data adapter, we're going to inherit from store database data and display data. So we're going to use both. We're going to have an init function that retrieves some data, self.data equals data. Okay, and we're going to define our store data. Okay, let's print a message to know that we are in this code. So call our code, but use third-party code. Okay, so we're adapting our code to the third party. And then we're going to say for item in self.data, we're going to convert the data type. So we're going to say DDT equals display data type. Okay, we're going to convert to float item.position. And then we're going to convert to a string the item.amount. Okay, so this is very specific to your code, to your functionality. In our case, we're converting the data that is passed to us, which is position and amount. We're converting that to our display data type so that we can call our show data. Okay, so with that, let's go ahead and say self.display data equals DDT. And we're going to call self.showData. Okay, so we're storing the data in the right way, which is required by the third-party library, and then we're just calling the functionality. You can see here that the specific call to the third-party functionality is encapsulated in our adapter, so the actual stored database data is not actually changed. Okay, so we're just adapting this call to the third-party functionality. All right, so with that, let's have a function here, def generate underscore data. Okay, and this will generate our list. So let's say data is going to be a list, and data.append database data type. We're just going to generate some data here. Let's say 2 and 2. Let me just duplicate this twice. And let's just change the values here, 3 and 7 and 9 and 1. Okay, so this is the data that we're trying to adapt, and we're going to return data. Okay, so now we have our main implementation. We're going to instantiate the adapter equals display data adapter. And here we're going to pass the generate data. And then finally adapter dot store data. Okay, so we're calling our functionality, but in reality, we're using the third-party functionality. Okay, let's just remove a few lines here so that the compiler is happy. And then I'm going to run the adapter. I think I just made a mistake here. We don't actually need this call here since we have the self.data. Okay, so just remove that, try it again, and run. Okay, another small mistake. Instead of display data type, we're not actually creating. We need to create our own data type. So instead of display data type, we're going to have database data type. My mistake there. Okay, so basically we are using our own code. We're not using the third-party code. The third party is going to be restricted to the adapter. So this has to be a database data type. All right, let's run it. And then we get our correct functionality. So we are calling our code, but using the third-party code, and third-party functionality has been converted, right? So our data converted to this data type. All right, that is it for the adapter pattern. Thank you for watching. I will see you in the next video. All right, so let's now talk about the bridge pattern. Now, the bridge pattern is very useful when we have multiple inheritance in our code. So you can imagine a part of our code, a class that needs to inherit from multiple other classes, multiple components. That class will be composed of a certain number of other parts and other components. The issue here is that the more of these components we have in our class, the more this class needs to handle different functionality in different cases. So separation of concerns is kind of broken here since one class will handle multiple aspects. So let's have a quick theoretical diagram to kind of illustrate this point. So here I have a class that inherits kind of two components. One is going to be shape and one is going to be color. So this will need to handle basically all these kind of permutations, right? Red circle, blue circle, red square and blue square. A better solution in this case would be to kind of separate these two components, shape and color, into their own classes. And you can imagine here if we add another dimension, 1, 2, 3 other dimensions, then this inheritance will kind of grow exponentially, right? So the better solution is to separate these two components. One is going to be shape, and that's going to handle circle and square, and another is going to be color, red and blue. And here we have the relationship between the two, which is what we call the bridge. Okay, so having classes with multiple orthogonal traits, multiples of these components, exponentially increases the size of the tree, right? So the more we have dimensions here, the more we have permutations down below. At its most basic, the bridge pattern converts from inheritance to composition. So we no longer inherit from multiple components. We compose them in our class and let each component kind of manage its own state and its own functionality. We split into multiple interfaces and multiple classes. As we've seen here, instead of having one that handles everything, we have two that are composed within our code. And then finally, we associate them using a bridge reference. Okay, now this is kind of a theoretical introduction. Let's move to code and see how that works in practice. All right, so here I'm going to create a new Python file called bridge. All right, now the first thing I need to do is from ABC import ABC and abstract method. I want to be able to set a few abstract methods in my upper class, in my main class. So here I will define class device. All right, so to give you a description of what we're going to do here is we're going to have a few different types of devices and a remote control to control those devices. And we're going to connect them through a bridge. Okay, so the first thing we need to define is the device. That's going to inherit from ABC. We're going to set a volume variable equal to 0, and we're going to define an abstract method, def get name. Okay, and here we will simply return a string. Now, since this is an abstract method, we're going to pass for now, and we're going to use this class in our inheritance. So class, first of all, let's say we have a radio that is a device, and here we have get name, and we will return an f string, something like radio self. Okay, very simple. Now let's define another one that's going to be TV, which is also a device. We're going to override the abstract method, and here we will return an f string, TV self. Okay, quite simple and straightforward so far. Now let's define the remote class. So class remote, ABC. And here we will have two abstract methods. The first one is going to be def volume up. Okay, we're going to pass since we are in the abstract class. And then we're going to define another abstract method, def volume down. And again, pass. Okay, so now we have the remote base class. We're going to define a class basic remote, which is going to be a remote. And we're going to define an init method where we pass the device that this remote is for. Okay, so here we have our device. You will notice here that we don't really specify which particular device it is. We can pass whatever device we like. So here we're just going to store self.device equals device. All right, now let's implement the abstract method. So volume up, and that's going to be self.device.volume plus equals 1. And then print an f string. We're going to say self.device.getName. Okay, volume up. And then we're going to print out the volume, self.device.volume. All right, so that's volume up. We're going to define volume down in a similar fashion, self.device.volume minus equals 1. And then let me just copy this code. And then we're going to say volume down to this level. So that is basically all we need to do. Now let's define a main function. And here we will have a radio and a TV. Okay, and of course we need two remotes, one for radio and one for TV. So radio remote equals basic remote of our radio, and TV remote is going to be basic remote of TV. All right, so we have those. Now let's go ahead and change up the volume a bit. So radio remote dot volume up. Okay, we're going to say radio remote dot volume up, and finally dot volume down. Okay, and we're going to do something similar for TV remote dot volume up, TV remote dot volume down, let's say. Volume down, and then let's say TV remote dot volume up, and duplicate that. So just kind of randomly changing the volume for those two. So you can kind of see how we work here. We have our basic remote and we have a bridge to our device. Okay, so we connect those in this way, and we can manipulate them regardless of which particular type of device we pass here. Okay, so if I run the bridge, then I would get the radio, volume 1, 2, and then back down to 1. The TV 1, then back to 0, and then increase it twice. Okay, so hopefully this gives you an idea of how the bridge pattern works. We have only two dimensions in our case. We have device and remote, but you can imagine a code where we have multiple of these dimensions. And in this case, the bridge pattern will be even more useful than it is here. All right, so the composite design pattern is often used when we need to apply a certain functionality to a structure in our code. And most often that structure is going to be a tree of components within our code, right? So let's have a look at a quick high-level example here. So here we have a computer that is composed, among other things, of memory, hard drive, and a processor. And the memory itself is composed of a random access memory and a read-only memory. And you can imagine this kind of tree structure going much deeper. Each of these components can be subdivided into other components and so on and so forth, right? But I've simplified it here to just a tree that looks kind of like this. Now, each of these components has a price, okay, a price assigned to it. And what we would like to do is we would like to calculate the total price for that element, for that computer. Or individually, we want to calculate the price for the subtree. For example, the one we have here is the memory, right? So we want to calculate the memory price, and then we want to calculate the computer price. And this is where the composite design pattern comes in, because we can apply one particular functionality, one calculation to the entire tree or to a sub-tree within that larger tree. So the composite design pattern allows us to structure objects into trees. And then it works really well when the functionality can be represented as a tree. So whenever we have this kind of structure, it can be a tree, it can be a graph. As long as we have a way of navigating that structure, then we can apply the composite pattern. It allows us to manipulate multiple objects as a single one. So for example, here it allows us to either manipulate the entire structure as one, as the computer, or if we want a sub tree from that larger one, we can manipulate the memory, for example, as a single element. All right, so that is the composite design pattern. I know this is kind of abstract, but let's go to our editor and start to implement an example of how this might work. So I'm going to create a new Python file here, and I'm going to say composite. All right, now the first thing I need to do is I need to define a class equipment. And by the way, we will implement the structure that we saw in the theoretical example, right? So we'll have a computer, memory, hard drive, processor, and so on. All of these are equipments, okay? So I'm going to define here an init that has a name of type string and a price of type int, okay? We're going to limit our prices to integers. And let's just store self.name and self.price. And that's going to be price. Okay, so that is my equipment. Now I'm going to create a class composite. Okay, let's define the init here. Now here I'm just going to provide a name for my composite, self.name equals name. I'm also going to define a variable, self.items is going to be an empty list. Okay, so we're just going to store the items that this composite is made up of. And the composite can be the computer that we talked about, or can be the memory, basically the tree nodes, okay, in our example. So here, I'm going to define an add function with a equipment of type equipment. Okay, and I'm going to say self.items.append my equipment. So we're going to store it in our equipment, and then I'm going to return self. Okay, so we can kind of chain the operations together. Now I'm going to define here a at property. Okay, and the property is going to be def price. Okay, we have self, and then we can simply return a sum. I want to return the sum of the equipment elements. Okay, so the sum of elements in this array, and I'm going to have x dot price, okay, for x in self dot items. Okay, so a list comprehension here, and we're going to sum everything together. Okay, now we have the price, and I'm going to have a at price dot setter, and I'm going to define price of self and value. Okay, self dot price equals value. Okay, so we're just going to store that value here, that price value. Okay, so that's pretty much all we need to do, and we're going to simply define composites and add elements to it, add equipment to it. Okay, so let's create a main function, and here we have a computer is going to be a composite. We need to provide a name, so I'm going to say PC, and we're going to have a processor that's going to be an equipment. Here I have my name processor and the price, let's say 1000. Okay, now I have my processor. Let's define hard drive is going to be another equipment of a hard drive, and this is going to cost 250, let's say. We're going to need to define the memory. Now the memory is going to be another composite. Okay, this is a node in a tree. It's not a leaf yet in our structure. So here we have memory, and we have ROM memory, which is going to be an equipment of read-only memory. And let's say this is 100. And finally, we have RAM, which is going to be an equipment random access memory, and that's going to cost 75. All right, so we have all the components. Now let's add them to create kind of the tree structure. We're going to say mem equals memory dot add. We're going to add the ROM and dot add RAM. And then finally, the PC is going to be computer dot add. We're going to add the processor dot add hard drive dot add the memory. Okay, so that's pretty much all we need to do. And now, since we have all the structure in place, we have the composite design pattern in place, we can simply say print PC dot price. Okay, so the PC dot price will basically calculate everything for us and just print out the price of this whole system. Okay, so let's go ahead and run this. And that is 1425. Okay, so what you can see here is that we have created our structure, and we automatically apply one functionality to the entire structure. We can apply the price to memory or to the PC itself. Okay, so that is the composite design pattern. All right, the decorator pattern, also sometimes called the wrapper pattern, is another pattern that is quite easy to understand and really, really useful in practice. What it does is allows us to update or modify the behavior of a class that we do not have control over. So you can imagine a class that is part of a third-party library that we cannot modify. However, we do want to alter its behavior slightly, or perhaps add a bit more functionality than is currently available. In that case, we can use the decorator pattern to add that kind of personalization to that third-party class. So in simple terms, it allows us to attach new behavior to an object that we do not control. Also, it allows us to do that without altering existing code. So of course, if the class is part of a library, we cannot modify it. So we want to be able to update it without altering the code of the class. When I say attach new behavior, I also mean, so on the one hand, attach new behavior, but also modify existing behavior that doesn't really suit the current requirements. Overriding behavior. So changing existing behavior that is present in the class, but we want to update it for our current purposes. So to kind of give you a quick theoretical example, we can imagine here we have a network communication system where we have a lower layer TCP/IP communication protocol. And let's say, as an example, that TCP/IP protocol has a send packet functionality. Okay, so that send packet functionality will not be enough for the purposes of our application. Okay, we want to communicate easily, seamlessly with a library, with an API, let's say. So we want to add some more functionality to this layer. So we can imagine that we can create a network communication layer where we have a send network message that uses the underlying send packet functionality. Okay, we have put a wrapper on top of this TCP/IP. And we can actually keep going. We can create another layer that is, let's say, an API service that we can actually use in our code, in our application, where we can say something like retrieve API that will kind of hide the details of the implementation, but just give us the required functionality for our code. Okay, so you can see how we can wrap or decorate lower layers and lower functionality into more abstract and more higher, let's say higher level functionality, okay, in kind of these layers. All right, so that is all for the theoretical introduction. Let's take a quick code example to kind of solidify how this works in practice. Okay, so let's go ahead and create a new Python file here, and I'm going to call this Decorator. Now, what I would like to do here is I would like to build a kind of an abstract example where we have a coffee machine that produces some coffee. And since we are, let's say, opening a coffee shop, we would like to have a bit more kind of fancy functionality where we create better coffees than just simple basic stuff. Okay, so let's go ahead and implement that and see how it works. First of all, I would like to import from ABC, import ABC and abstract method. Okay, we want to create abstract functionality here. So first of all, class coffee machine that inherits from ABC. Now this will have two abstract methods. So first one, abstract method def make small coffee. Okay, I'm gonna have pass for now. And another abstract method, def make large coffee. Okay, again, we will pass. All right, so this is my abstract functionality. Now this, we're gonna say it's a third-party library. We don't have access to it, okay? What we want to do is we want to wrap this coffee machine in another layer that uses the functionality that we've defined here, but also adds its own functionality or maybe overrides some behavior. Okay, so let's create a class basic coffee machine. Okay, here we will have a inherits from coffee machine here. All right, now this one will simply implement the two abstract methods. So I'm going to have def make small coffee. Let me change that real quick. Small coffee. Now here I'm just going to print basic coffee machine making small coffee. And then I would like to define a make large coffee, print basic coffee machine making large coffee. All right, so this is the implementation of my abstract class. Now, we would like to override this functionality. So let's say enhanced coffee machine that inherits from coffee machine. All right, so importantly here, if we're going to wrap this functionality, then we need to provide this object to my enhanced coffee machine. So I'm going to have an init where I can pass basic machine of type basic coffee machine. Okay, and I'm going to store this self.basic machine equals basic machine. All right, so we have the object, and this is going to be the wrapper on top of the object, or the decorator of this basic coffee machine. So what I would like to do here, since we inherit from coffee machine, we need to implement the basic functionality. So def make small coffee. Now here, we can simply use the functionality that the initial object, the underlying object, gives us. Okay, so for this example, we're not going to do anything special. We're just going to use self.basicmachine.makesmallcoffee. This is to kind of show you that we can have some functionality that is there, and we're going to use it as it is in the lower layer. Now, if we want to override some functionality, we're going to override make large coffee self.basicmachine. So for the large coffee, let's override the functionality, right? So instead of printing the basic coffee machine message, we're going to print the enhanced coffee machine making large coffee. Okay, so that is the alteration. That's the change in functionality. Okay, we can see that it's different. We print a different message. Now we can also have added functionality. Okay, so we have same functionality, change functionality, and added functionality. Let's say make milk coffee. Okay, so for milk coffee, we can use some of the underlying lower level functionality, but add our own. So here I'm going to have print enhanced coffee machine making milk coffee. Okay, we can use self.basiccoffeemachine.makesmallcoffee. So we're using the functionality, but we're adding a bit more. So print line or print enhanced coffee machine, let's say adding milk. Okay, so we're kind of wrapping this lower level functionality with our own custom one. Okay, so that is the example. Now let's move on to the main and call these functions. Okay, so here I'm going to have a basic machine is going to be equals basic coffee machine. And then the enhanced machine is going to be enhanced coffee machine. And here, of course, we need to provide the basic machine. Okay, so we have the two. Now I'm going to call enhanced machine dot make small coffee. Let's just print one line here. Enhanced machine dot make large coffee. Print an empty line again. Okay, and then enhanced machine dot make milk coffee. Okay, so that should call all the functionality that we have defined. So let me just run the decorator now. Now, the first one, simple functionality that's defined in the lower level, updated functionality or overridden functionality. And then the final one is kind of decorated. So we have some functionality before we call the lower level class, and then we add some of our own functionality afterwards. Okay, so we've kind of wrapped the existing functionality into our own code. All right, so hopefully that's clear. That is how the decorator pattern works. In this video, we will talk about the facade pattern. Now, this is one of the most useful design patterns because what it does is it allows us to hide away some complexity and some difficult to understand functionality behind a very simple interface. Okay, so let's have a look at what it is. Basically, it allows us to provide a simple interface to complex functionality. You might have a third-party library that has some complex inner workings, or you might yourself develop a library that you want your clients to use there is no reason for the client to understand all the complexity that goes around the functionality that you're trying to implement. What you're trying to do is simply provide a way to use that complexity. Okay, so you want to provide an easy interface, an easy facade to allow a client to use a particular system or a particular piece of code. And it removes the need for complex object or memory management. The facade itself is not a simple interface. It is let's say, a class that provides some functionality. However, it manages all the complex object or whatever memory or data types or whatever it is. It manages that within your class and provides an easy way to access the underlying system. And it simplifies client implementation, of course, since the client doesn't need to understand how the third-party library works or how the system that you're hiding behind the facade works. Then the client is much simpler. And of course, this provides us with separation of concerns, since the client doesn't need to know how you implement something. It just needs to know how to call that particular something. All right, so that is the quick introduction. Let's have a look at some code to see how this works in practice. So here, let me define a new or create a new Python file that's going to be called Facade. All right, so what I would like to do here is I would like to create a kind of quote unquote simulated storage system and store some data. Okay, in our case, it's going to be some user data, and we're going to provide a facade for that user storage system that hides away the complexities of that implementation. All right, now here, I'm going to create a class complex system storage. Or store, complex system store. And we're going to define an init that takes a file path of type string. Now, a few variables here. Self.filePath is going to be file path. Okay, this is where we're going to store the data in our system. Self.cache is going to be a dictionary. So we're going to provide a caching functionality with this complex system store, and we're going to just print a message here. Let me just make that an F string, reading data from file. And here I have my file path. All right, now we're going to define a store functionality with a key of type string and a value of type string. And we're simply going to say self.cache of key is going to be value. Okay, easy enough so far. Now let's define a read with a key of type string, and this will return self.cache of key. Okay, we're going to be able to read from that cache. And finally, def commit. We're going to have simply print line, an F string storing cached data to file, self.file path. Okay, so this is the complex system store, and let's define the type of data that we will be storing. I want to just add here at the top from data classes, import data class. Okay, so that we can define data classes in our code. So here I'm going to define a data class, class user, and I'm just going to have a login of type string. This is, of course, very just an example for us. So I'm not going to put too much effort into adding complexity. We can simply keep in mind that this is a complex, quote unquote, complex system store, even though we haven't implemented much complexity here. This is a third-party library, or it can be defined in our own application, but we just want to kind of shield the user from using such complexity and understanding the inner structure. Okay, so for that purpose, I'm going to have a facade here. For the facade, I'm going to define a class user repository. Okay, so the user repository will allow us to store users with our caching system on a file path. Okay, so class user repository. Here I'm going to define my init, and let's say self.system_preferences is going to be a complex system store, and let's give a file path. So something like data/default.prefs. All right, so that is my init. Now let's define a save function where I have a user of type user. So I would like to be able to save this user on the complex system store. So self.systempreferences.store. I'm going to define a user_key and user.login. Okay, so I have stored this and I want to commit. So self.systempreferences.commit. Okay, and then finally we have find first. Okay, and here we want to retrieve a user. So here we will return user of self.systempreferences.read, and I want to read my user key. Okay, so I'm just going to retrieve the first. We can imagine a system that stores multiple users. I want to just get the first one that is available, and I read it with my key that I have defined. Of course, again, here we are simulating some real system. In reality, you would have a lot more complexity here, obviously, but we're just going to limit it to this. So main. Here we want to just use our facade to store and retrieve our user. So user_repo is going to be a user repository. Okay, we're using the facade, and we will have a user, let's say John. Okay, so we're just going to store and retrieve this user in our repository. So user repo.save my current user. So I have saved it in my repository, and I want to retrieve it. So retrieved user is going to be user repo.find first. That just retrieved my user, and I can just print my retrieved user.login. It should be the same as the one we defined here. All right, so that is my functionality. That is my facade. You can see in my main system, in my client code, I am only using the facade. I am not actually using the complex system store. That is hidden behind my user repository facade. So let's go ahead and run this code. And we can see, first of all, reading data from file default preferences. This is the init function. Then storing cached data to file. Okay, that is the commit functionality. And then we are retrieving the user. And just to confirm that we have retrieved the right user, we are printing the login, and we have John that we have defined here. So that is how, on a very high level, you implement the facade. All right, so let's talk about the Flyweight design pattern. The Flyweight design pattern, as its name suggests, is all about reducing the load or the requirements on a system. So for example, on a memory system, it reduces the amount of stuff that you store in memory. In a processing system, it reduces the amount of processing that you might want to do. That is where the name Flyweight comes from. So let's have a look at a quick kind of abstract example to give you an idea of how this works. So let's say we have a system that has some limited memory capacity, right? Let's assume we are in some sort of game where we want to produce elements on a screen and we want to display them. So one kind of naive implementation would be to create as many objects as we require and store them in memory as they come up. okay, and remove them as they get destroyed. So you can think about a kind of a war game where you have soldiers that come up on the screen, and you want to store every single soldier. You want to store them in memory when they are visible. Okay, so that is how this might look, but of course, this is kind of an inefficient way to go about it because that will fill up the screen quite quickly. Okay, a better implementation would be to have some sort of shape factory or kind of character factory or element or whatever that simply produces elements that are required, that are unique, and then you use those elements in memory as a more efficient solution, right? We don't want to create the same functionality over and over again. We just want to display it whenever we require, and just store it in one place as a single entity. Now, of course, this doesn't work for everything. So if we take the example of our war game, you could store the sprites that are required to display the elements. You could store them in a factory. However, you might want to have elements for every single quote unquote soldier or character on the screen. You have unique information related to that character. So for example, the direction where they're moving, or whether they are firing or hiding or whatever it is, the state of that element, you still have to uniquely store it for that particular character. However, the stuff that you can store in the stuff in common, like the sprites, you can and should store them in a central location. So that is where the Flyweight design pattern comes in. It works when you have a lot of similar objects that can share some functionality. The functionality that they share can be unique, okay? The functionality that you cannot share has to be individual for each individual element. It allows us to reduce memory footprint in our example, but it also allows us to reduce processing footprint, right? You don't have to kind of retrieve from memory and process those sprites over and over again. You just have them already ready to go and just grab them whenever you need to. And of course, it allows us to improve efficiency. We don't want to, if we have a large amount of elements in memory, retrieving them and displaying them and updating them does take a lot of time. So efficiency is quite important as well. Okay, so Flyweight helps with all of that. All right, so that is all for the theoretical introduction. Let's have a look at some code. And I would like to implement here a system where we have some sprites and some characters that have different ranks. Okay, we saw the example of 3 types of elements. We're going to implement 3 types of characters in our code. So let's go and create a new Python file, and I'm going to call this Flyweight. All right, and first of all, I'm going to import random. We're going to need this to create some random characters, and I'm going to import from ABC, import ABC and abstract method. Okay, just to create abstract classes. So first of all, we're going to have a class sprite with ABC, and here we will have an abstract method that we can define as draw. Okay, pass for now. And then we're going to have another abstract method, define move. And we're going to provide the coordinates, x of type int and y of type int. And here we're going to pass again for now. Right, so let's define a class fighter rank. Okay, so we're going to have 3 types of fighters. Let me just spell that correctly. 3 types of fighters in our code. We're going to have a private. Let's give it the value 0. We're going to have a sergeant, value 1. And we're going to have, let's say, major, value 2. Okay, so these are the types of fighters. And let's create a class fighter that inherits from sprite. All right, so here we're going to define, first of all, our init or override our init. We're going to pass the rank Okay, and we're going to store that self.rank equals rank. All right, so let's implement the fighter. This is a sprite, so we need to override these two methods. So first of all, draw. For the draw, we're simply going to print a message, an f string drawing fighter, and I'm going to have the self here. And for the move method, we're also going to print an f string. Okay, and here moving fighter self to position x, comma, y. Okay, so very kind of abstract implementation, but it gives us the kind of picture of how this might work. Now, let's define a class fighter factory that will allow us to create fighters. So first of all, let's override the init. And here we're going to just have a self.fighters is an empty array. And we're going to have a function get fighter with where we provide the rank of type fighter rank. All right, so here we're only going to store three actual fighters, one for each type. Okay, so first of all, we're going to say f equals self.fighters of rank. Okay, so we're going to try to retrieve the fighter with that particular rank. Now we're going to say if not f. So if we don't have one, then we're going to create it. F equals fighter of our rank. And we're going to store it for later use. So self.fighters of rank equals f. Okay, and then finally we will return f. So again, here we have our fighters. The fighters will eventually have only 3 elements, one for each rank that we have. All right, so that is pretty much it. Now let's create a class army, okay, with a self.army is an array. Sorry, just define the variable here. We don't need self. Now, I'm going to define spawn fighter with a rank of type fighter rank. And here we're going to say self.army .append. Now, keep in mind that this will not contain unique fighters. They will just contain the ones that we have here. Okay, so here we have fighter of rank. Okay, so we're adding fighters to our army. And then finally, def draw army. Okay, and for fighter in self.army, we're going to say if fighter.rank equals fighter rank dot, let's say, major. Then we're going to say print. I'm going to print an M, and I'm going to define the end equals empty string so that everything gets printed on a single line. Elif fighter dot rank equals fighter rank dot sergeant. In that case, I'm going to print S space with an end empty string, and then else print a P space with an end empty string. Okay, so our army will be printed on a single line. All right, now we have our main. Okay, and army underscore size is going to be, let's say, 1000 to start with. Then army equals army. Okay, so define or instantiate the object. And here for I in range of army size. Okay, R equals random dot rand range, hard to pronounce that. Here we have 3. So since we have 0, 1, and 2 as fighter ranks, 0, 1, and 2, we can get a random number from here. And then we can say army.spawn fighter with our R. And then finally, we just need to say army.draw army. Okay, so hopefully that will work if I haven't made any mistake typing. Let's go ahead and run this. And then we get our army. So we have private, sergeant, and we have major. Okay, so we can see here that this is quite efficient. Obviously, even if we created individual objects for each one, we have 1,000 elements. It's not that many, but in a real system where each element does have to store some local state, this is much more efficient. So everything that we can share between the elements, we want to share it as much as possible. And we do that in our case in the factory, okay, where we have only 3 types of fighters, but we just create as many as we require for our army. Okay, this is the shared functionality. And we can actually increase this to, let me just comment this out. And if I put army size equals 1 million, we can actually run this as well. It just takes a bit of time and then it just displays everything. Okay, so again, for a modern system, this is a very quick program, but in reality, where we have many elements on a screen, we can think of a game, but there are other situations where we might have that. This is a way to reduce the memory and processing footprint. In this video, we will talk about the proxy design pattern. Now, the proxy design pattern will allow us to have an interface or kind of an object in front of an existing object in our code. The point of the proxy is to kind of manage the lifecycle and the access to the underlying object. Now, why might we want to do that? Let's take a quick example. Let's say we have a disk management system that, let's say, might take quite a bit of time to access the functionality underneath, to access files, to retrieve them, to store them, update them, and so on. And let's say we have a bunch of clients that are trying to access the disk more or less at the same time, creating files, writing, reading, and so on. So immediately you might see a few problems with the system. First of all, since the disk takes a bit of time to retrieve the information required, all the clients accessing the disk at the same time might overload the system and lead to a lot of delays. Furthermore, accessing the same file at the same time from multiple clients might lead to inconsistencies in that file. If we're trying to write on the same file at the same time, then that might cause a problem. So one of these solutions might be to implement a disk proxy in front of our disk. Okay, so this disk proxy might provide some, let's say, caching functionality to try to speed up the system, right? So if multiple clients are trying to read the same file at the same time or subsequently, then we might provide the cached version of that file rather than accessing the disk every single time. Also, we might provide some sequencing operations where if we're trying to write the same file at the same time, the disk proxy might make sure that the written file is consistent. Okay, so the sequencing is quite important, and we want to remove that from that disk since the disk might already be doing a lot of processing to retrieve the information. All right, so the proxy, in brief, just provides some functionality before or after calling an object. So we might want to provide functionality before, after, or instead of the underlying object. Importantly, for the proxy, it provides the same interface as the original object. So here, the accessing system, so in our case, the clients, do not actually know they are talking to a proxy rather than the disk, and they actually don't care, okay? As long as the information is consistent, the proxy might just, they might access the proxy instead of the real disk without actually realizing it. Now, there's a couple of similarities with other design patterns. So the proxy pattern is quite similar to a few other patterns, but there are some important differences. First of all, the proxy is quite similar to the facade design pattern. The important difference here is that while in the facade we provide a simple interface to a complex system, the proxy has the exact same interface as the object that it is kind of hiding, right? So the clients in the proxy case do not actually know they are not talking to the actual object. They think since they are accessing the same interface, then they think they are talking to the real object, even though they are not. In the facade, they know or they're actually accessing an interface that is a simplification of the functionality underneath. In addition to that, we have a similarity with the decorator pattern. So as we've seen, the decorator pattern can also override, can also replace the functionality underneath. The difference here is that the proxy manages the lifecycle of the object that it is hiding, okay? Whereas the decorator simply replaces some functionality or adds its own before or after, the proxy actually uses the underlying object every single time and manages the lifecycle of its object. So quite a subtle difference, but an important one. All right, so with that said, let's move to our code and create or write an example for the proxy pattern. So let's create a new file called proxy. And what I would like to do here is I would like to have a image object that might take some time to display. And I would like to have a proxy image that adds some functionality on top of it. Maybe something similar to caching the image. All right, so I'm going to first of all import from ABC, import ABC and abstract method. ABC and abstract method. Okay, and I'm going to define a class image with ABC and abstract method def display. Okay, and I'm going to pass for now. So the image, the object underneath is going to be an image, and we're going to call that real image, which is a type of image. Okay, and here let's define or override the init first, where we provide a file name of type string, self.filename equals file name, and let's print a message, real image, loading, and we have our file name here. Okay, in addition to that, let's define a display, or rather override the display from the abstract class. And here we're going to print again an f string, real image displaying self.filename. Okay, I'm going to just add an and with 2 lines here, just to kind of have a bit of separation there when we actually display the image. All right, so let's define here a proxy image that is also an image. Okay, proxy image will have an init that has the same signature as the other one. So we have a file name of type string. We will store self.filename equals file name. And we also want to store self.realImage is none for now. Okay, so we have our proxy image. Of course, we need to implement the display. And again, here we have the same signature, but the functionality will be quite different. So first of all, let's print a f-string proxy image displaying. And here we have self.filename. Okay. If not self.realImage, so if we don't have anything stored there, then we can simply print from disk. Okay, we are retrieving the actual information for the image from the disk, and we say self.realImage equals real image of self, without the quotes, self.filename. Okay, however, else we will print from cache. Okay, so if we have accessed this before, we just display it from the cache. And what we want to do here, we say self.realimage.display. Okay, so a very basic caching functionality. All right, so that is all we need to do. We have implemented our proxy. We just need to call everything we need. So first of all, image is going to be proxy image. Okay, let's say test.jpg. Okay, now here, first of all, let me put a comment, load image from disk. Okay, and we say image.display. Then the second time we call that, we will say load image from cache. Okay, and we will get the confirmation when we actually run the code, since we will print out the correct information in the code. So let's go ahead and run our proxy. The first time we run this, we get proxy image displaying, we get it from the disk, real image loading, and real image displaying. However, the second time we run, we get proxy image test, that is standard, but we will get it from cache this time. We are no longer loading because we have it loaded already, and we are just displaying it. So you can see it's faster. The functionality is more efficient. Of course, we are just simulating here. We're just displaying a message, but you can imagine loading an image from the disk, or let's say from an API, might take quite a bit of time. So this printout here, in reality, in a real world system, might take quite a bit of time, and we just remove it, remove the necessity for it when we are displaying the image for a second time. So that is the use of the proxy design pattern. All right, in this video, we are talking about the chain of responsibility design pattern. So we're going to start with a quick diagram to show you what kind of conceptually high level what this design pattern is about. So here we have a chain of handlers, which are classes or objects or components that can handle a specific request. So what we do here is we pass some sort of request to one of the handlers. The handler will process that request in some way, and then it has two options. First of all, it has a link to the next handler in the chain, so it could pass the request down the chain, or it has the option to kind of quote unquote consume that request and return a result, thus skipping the rest of the chain. And if the request moves on to the next handler does the same thing, either processes it and consumes it, or simply hands it over to the next handler, depending on the logic that is implemented in that particular handler. Okay, so you will find this pattern quite often in various systems where you have multiple components in your system that can handle a specific request. So to kind of sum up, we define a chain of handlers to process a request. Each handler contains a reference to the next handler. So we can pass that request to the next one, and that is how we actually create the chain. Okay, each handler moves the request down to the next handler. The handler decides whether or not to process the request. Okay, it has the option to skip it entirely. It has the option to consume the request and return a result, or it has the option to do some processing and pass it on to the next handler in the chain. And then we can have different types of requests. So we can have some requests that start from the beginning of the chain and move down all the way to the end. We can have requests that start somewhere in the middle of the chain and then go forward with the next elements in that chain. Okay, various types of requests, various types of handlers. All right, so that is the introduction to the pattern. Let's go ahead and implement an example here in code. So let's create a file chain of responsibility. So what I'm going to do here is I'm going to implement a system that can add, we're going to assume that we pass some network request to our chain, and our chain consists of handlers that can add headers to that network request. So we're going to have, for example, an authentication header. We're going to have some body payload header and so on, right? So each header can have the option to add something to that request. All right, so first of all, let's import some elements from __future import annotations. Okay, this is because I would like to use some classes in a random order, maybe before they are defined. And then from ABC, import ABC and abstract method. Right, so first of all, let's define our handler chain class. Okay, this inherits from ABC. And here we're going to override the init method to provide an input header as a parameter. And this is going to be a handler chain. Okay, and here next header is going to be the input header. Let me just type that, spell that correctly. Input header. Right, so let's define an abstract method, def add header, with an input header of type string. We're going to pass, and then we're going to define a do_next method with an input header of type string. Okay, so the input header is basically where we add our functionality, our data for this particular header. So here we can say if self.nextHeader. If we have a next header, then we will return, we will pass it on. So we will return self.nextHeader.addHeader with input header, and then return input header. So if we don't have a next header, we just return the result. If we have one, then we invoke the add header with the information that we have here. All right, so let's define a class. And here we're going to implement some handlers. Okay, so we're going to have authentication header with that inherits from handler chain. That's going to be part of the handler chains. And we're going to define an init method with a token of type string. And we're going to provide the next header of type handler chain. We're going to have none by default. Okay, so we're going to first invoke the super method dot init with handler chain with next header, that's the name. Okay, and then we're going to say self.token is going to be equal to token. All right, so that is the instantiation. So we're going to implement the add header method. And here we can simply say h equals an f string, input in curly brackets, input header. So what we have already received /n, and here we're going to have authorization : self.token. Okay, so we're just adding our information to the existing header, and we're going to return self.doNext. with H. Okay, so that is the authentication header. Let's create another one. We're going to have content type header. Okay, this is also part of our handler chain. Again, we're going to have our init method. And here we're going to pass some parameters, content type of type string, and of course, next header of type handler chain. That's none by default. Okay, let me just make some space here. Right, so for the init, it's very similar. We're going to add the super call and then self.content type equals content type. Right, so now we have to implement the add header method. And here we just add our content type information to the header. So H equals an F string with our input header. Okay, /n content type one word colon space self dot content type. And then we're going to say return self dot do next with H. Okay, and just for fun, so that we can have three handlers, let's add another one, class. And here we have body payload header, right? Which is a handler chain as well. Very similar. I'm going to override the init method. And here we're going to pass the body of type string and next header of type handler chain is none by default. The super method call and then self.body equals body. Okay, now the add header, that's going to be slightly different from the others. Here we're going to have H is an F string with input header, and we're going to have /n, and here we just put the self.body. Okay, this is not a header anymore. This is the body of the request, and then we can return self.doNext with H. All right, so hopefully that is enough. So now we have three elements. We need to instantiate them and arrange them in a chain and then call some requests on them. So let's implement the main. Authorization header is going to be authentication, or we should call this authentication, even though the header itself is authorization, the class is called authentication. Okay, authentication header, and here we can pass some information, some token, 1, 2, 3, 4, 5, 6. This is our authentication token. Then content type header is going to be content type header with, let's say, JSON. Okay, body header is going to be body payload header. And here we have some JSON. So let's say body colon and curly bracket. Let's escape the quote. Let's say username, escape a quote, colon, not colon, equals, escape a quote, and let's say John, and final escape quote. All right, so we have our three headers. We need to arrange them in a chain. So authentication header dot next header is going to be the content type header, and content type header dot next header is going to be the body header. Right, so we have our chain. Now we need a couple of requests. So we're going to have one request that goes through the whole chain from authentication to content type to body, and then a second request which skips the authentication and just goes through content type and body. Okay, so we're going to say message with authentication is going to be equal to authentication header dot add header for the message header with authentication. Okay, and we're going to have message without authentication equals. So we're not going to call authentication header, but we're going to call content type header.add header to header without authentication. All right, so that's all for now, and we just need to print the message with authentication. I'm going to print an empty line here, and then we're going to go print message without authentication. So let's see if I haven't made any mistake typing that. I'm going to run this, and then the first one is going to be header with authentication. So we'll get authorization, content type, and body. I forgot a curly bracket for the body here. Okay. Right, so I have the curly bracket, and then without authentication, we get JSON and the body. So you can see here that all these messages go through the chain. All the headers that we implemented will process the request and then pass it on to the next header until we reach the end. And we know that we reach the end here because we don't have a next header, so we just return the result. Also, here we have one request that goes through the entire chain, and we have another request that goes through only part of the chain because this one, for whatever reason, doesn't require authentication. So that is the chain of responsibility design pattern. Right, so the next design pattern we're going to talk about is the command design pattern. So let's have a look at a diagram, a high-level overview to see what kind of overall problem the command design pattern is trying to help us solve. So here we have a system that contains two parts. We have a GUI or graphical user interface, and we have some business logic, right? The GUI will be made up of some components, a few buttons, some text fields, sliders, and so on and so forth, right? Now, each of these components on the GUI side will want to interact with the business logic. There is a separation of concerns there. The GUI takes input from the user and invokes some requests, some functionality on the business logic. So that means this particular button will invoke some functionality here. The other button that we have will invoke some other functionality. The text field, let's say when it's updated, will let the business logic know, and so on. So all of these will call their respective functions on the business logic side. So immediately you can see a problem with this, and that is the tight coupling between the GUI and the business logic, right? So all the components here need to know exactly which function to invoke on the business logic side. This leads to tight coupling, which leads to low usability and a host of other issues, right? Like testing and so on. So, of course, we want to solve this problem, and we can solve it by introducing another layer between the two, and that is the command. So the command will simply take all the information from the graphical side in our case, will package that in some standard form, and it will pass it to the business logic. So immediately you can see here that there's no longer a connection between the UI and the business logic. Everything goes through the command, and the command kind of package will go to the business logic and will get processed. Right, so the request is wrapped in an object that contains all the required information, and based on that information, it can be later processed on the business logic. The command object is passed to the correct handler. So in our case, in this small example, we have a business logic layer that can handle commands, but obviously in a real world situation, we can have multiple components on the backend side that can all handle different commands. So the commands will be passed to the relevant business logic side. Or we can also have multiple servers of business logic, and we can have some sort of load balancer that sends commands to various servers to kind of make the system more efficient. Right, now benefits obviously include decoupling, as we've seen, but there are many other benefits such as efficiency. We can introduce some ordering if we require. Okay, so in our case, we have UI commands, but in a real world situation, we can package any type of information into an object that can then be processed, into a command that can then be processed. So we can implement some sort of ordering or some priority for the commands. Okay, all this is possible once we encapsulate this information. Otherwise, calling the methods directly simply won't allow us to do that. All right, so that is the theoretical introduction. Let's have a look at some code to see how we implement this in practice. So here we can create a new Python file command. Right, so what I would like to do here is I would like to implement let's say a restaurant or some sort of ordering system that can package the information the ordering information in a command and pass it on to some sort of processor for processing, right? So it's going to be obviously very abstract. We're just going to print some information, but the logic behind it is going to be sound. So first of all, from ABC import ABC and abstract method. Okay, and let's add the class command. Now the command will inherit from ABC, and we're going to override the init method where we pass a command ID of type int, and we're going to store that. So self.command ID equals command ID. And we're going to have an abstract method where we define an execute. And here we will simply pass. Okay, so we have the command ID and we have a way to execute it. That is our command object. Now, let's go ahead and implement a class order add command, which is going to be a command. And we're going to override the execute method. Here we simply print a message. Let's add an f string, adding order with ID self.command ID. Okay, we're going to assume that this actually executes the command that we have here. And then we're going to have a class order pay command. Okay, command. This can be an online shopping system or a restaurant or whatever it is. And here we will override the execute. So importantly, all the commands will execute in a similar way, right? So that will allow us to kind of implement this, let's say, ordering or priority system. Okay, so here I'm going to print an f string paying for order with ID self.command ID. Right, so we have our orders. We're going to limit ourselves to 2 order types, 2 kinds of commands. So I'm going to have a class, and let's call this command processor. Okay, and we're going to just define a class variable. Let me make some space here. A class variable called Q. Okay, an empty array. And we're going to have an add to Q of self and command of type command. Okay, self.q.append our command. So we're going to add the command and then we're going to process them. So def process commands. Okay, and we're going to have just a list comprehension here, item.execute for item in self.q. Okay, and then we're going to importantly set the queue to an empty array. So reset those commands because they have been processed. So that's pretty much all we need to do. Now let's go ahead in main, let's go ahead and create some commands and execute them. So first of all, I'm going to have my processor equals command processor. And let's add some commands. So processor.add to queue. Here we're going to have a order add command with order 1. Duplicate that and order 2. And so I have added 2 orders. Now let's pay for 2 orders. So processor.add to queue. What's the name? Order pay command of 1 and duplicate that and 2. All right, so that's it. And then we can simply call processor.process commands. All right, let me just remove all the white spaces here. Right, so that is all there is to it. So we have our queue and we have the execution. So let's go ahead and run this. Right, so we have adding order with ID 1, adding order with ID 2, then paying for order 1 and paying for order 2. So you can see here how we encapsulate that information, that requirement into a command class, and we pass that command class to processor. Okay, processor handles commands. It doesn't really care which kinds of commands, it just calls execute. So you can kind of imagine here we can implement a lot more complexity if our system requires it, where we order some commands, we execute them in a certain order, we balance them across multiple servers if we require, and so on and so forth. The interpreter design pattern is a pattern that's very useful when we're trying to have a system that can quote unquote understand or process a language. Now, languages don't have to be, human languages. They can be mathematical languages or some sort of programming system. However, the interpreter allows us to move through a quote unquote sentence in that language and understand it and do some processing on it. Now, this sounds a bit abstract, so let's start with an example. Let's say we have a mathematical, equation, right? So 5 plus 3, whatever that is. We have 4 main symbols here: plus, multiply, divide, and we have minus as well, although it's not included here. And we want a system that can kind of understand this expression, okay? So it can allow for the flexibility of algebraic equations using only these 4 symbols. So how do we do that? We can build a kind of a tree from these expressions. So first one is going to be, for example, here, we're going to take the last symbol that is a division and add the 2 components of it. On the left side, we have another tree. On the right side, we have the number 5. Now, on the left side, we can take the symbol multiplication and have a binary tree there as well. On the left side, we have some expression. On the right side, we have the number 2. Okay, so if we take the left side again, we have a plus symbol. On the left side, we no longer have an expression. We have this should be 5, right? 5 here, that's my mistake. But on the right side, we have the number 3. So we build this tree, this binary tree, with this expression that we were provided, and then we can have the system go through that tree in a binary way and calculate the result. Okay, so this is kind of an example, but this works very well with any other kind of quote unquote language, right? So we recursively evaluate grammar and expressions. Grammars in this case is going to be the symbols, and expressions are going to be the numbers. This works for parsing systems, for processing engines. So if you're trying to understand, the best example is a mathematical equation. A processing system that can cope with that will use an interpreter pattern. We have 2 main components in our pattern. One is going to be a terminal expression, which in our case are the numbers. Okay, these are terminal. And we also have non-terminal, which in our case will be these 4 symbols, or 3 in the case of this particular equation. So terminal and non-terminal expressions. All right, so that is the introduction. Let's have a look at a piece of code to see how this works in practice. So I am here in our editor, and I'm going to create an interpreter file. And first of all, I'm going to define an abstract expression. That's going to be a class. It will have a static method. Okay, and it will define an interpret that will simply pass for now. Okay, so we have expressions, right? Abstract expression. Now we're going to define two types of expressions. One are going to be terminal and the other are going to be non-terminal. So first of all, terminal expressions or expression, because that's going to have a class. Now in our case, the terminal expression is going to be the number, which is going to inherit from abstract expression. So let's override the init method and pass the value here for our number. Self.value is going to be, now let's convert this to float, since our expression will be able to give us floats, right? If we have division, then we can probably assume that at some point we'll have float values. Right, so this is the number. Now let's define an interpret or override the interpret. And of course, I need self here. And I'm going to return self.value. Right, so that is the terminal expression. Now let's define non-terminal expression. And that is going to be class algebra or algebraic. Let's call it algebra for short, expression. Algebra expression is going to be an abstract expression. We're going to override the init method. Okay, here we have two parameters, left and right. Okay, so let's just store that. Self.left is going to be left, and self.right is going to be right. Now, we're not going to add the interpret here because we will override that since it comes from abstract expression. We'll override that when we implement classes that extend from algebra expression, which we're going to do now. So we're going to have class add, which is an algebra expression. Okay, and we're going to define interpret with self. And here we will have return self.left.interpret plus self.right.interpret. Okay, so that is the add. Very, very simple. So we allow the left expression to interpret and the right expression to interpret as well. Often we will get the right expression is going to be just a number, which interpreted will just return the actual value. However, the left expression will require, recursive calls for this interpret. All right, so that is add. Now let's add subtract with algebra expression. And we're going to define interpret here. And we will return self.left.interpret minus self.right.interpret. Okay, very, very simple. We're going to have class multiply algebra expression. And actually, I'm just going to copy this and paste it here. And I'm going to have here multiplication. And then finally, class divide algebra expression. And I will paste that and make sure we change the symbol division. Okay, so these are my 4 algebra expression or algebraic expressions. So that's pretty much all we need to do. Now let's just go ahead and implement the main. The main will kind of contain a bit more information. Okay, so let's have a target expression here. That's going to be, let's say, 3 plus 5. Make sure you put the spaces in. I've set this requirement so that it's easier for us to kind of break down this expression into symbols, right? So space before and after every symbol, whether it's a number or a actual symbol. So 3 plus 5 minus 2 multiplied by 7 divided by 5, let's say, plus 11. Okay, whatever you want the expression to be, it doesn't really matter. Now, we have our tokens, which is going to be target.split, split by a space. Okay, so this will give us a list of tokens, and we have expressions is an empty array. Now, for I in range of length of tokens, okay, now here, if I equals 0, if we reach the end, we can say expressions dot append our this is going to be a number. So we know that always at the beginning we have a number. So we can just add it to our expressions, tokens of I. We can put tokens.0 here, it doesn't really matter. Any case, if tokens of I equals plus, okay? So if it's a plus, then we say expressions.append. Here we have an add expression. Okay, now we have expressions.pop. And the right side is going to be a number of tokens of I plus 1. Okay, so we know that after each, let me put a colon here. After each actual algebra token, we have a number. So we can just add it there. Okay, then if tokens of I is going to be minus, okay, we can do the exact same thing. So let me just copy and paste that, except this is a subtract. Okay, let me make sure we haven't made any mistake. I think it's fine. Then if tokens of I equals multiplication, then we have, instead of add, we have multiply. And then we have if tokens of I equals division. We need some quotes there. Okay, then we have divide. Right, so we have all the information. We have constructed our expression, so we can just call result is going to be equals expressions dot pop dot interpret. Okay, and then we can hopefully print the result here if we haven't made any mistakes. So I think that is all there is to it. Let's run this code and see if it works fine. Yes, 19.4. So that works fine. Now, there might be some edge cases which I haven't verified. So for example, if we just provide a target of a single number, you can check that. But the main idea here is that if we provide this kind of expression in a certain format, an algebraic expression, this interpreter pattern will go through it recursively, build the expressions that we've defined, and apply the interpret function to each one recursively and give us the final result. Okay, so hopefully you see how the interpreter pattern works. All right, next on our list is the iterator pattern. Now, to be fair, if you've been a developer for more than 5 minutes, you've probably already used Iterator in your code. Okay, so you probably already know what the iterator is. I have included it here for completeness, but also because I want to show you an example of how you might implement it yourself if you want to, if you have a requirement for it, right? So an iterator is basically a way to traverse a collection, to go element by element and apply some functionality to it, or simply return it for whatever purpose. It has two methods. First is going to be the hasNext, which will return a Boolean on whether or not there is anything more in that collection. And then next will actually move to the next element and retrieve and return that element. Okay, so very simple, very intuitive. We already know how this works, but let's go ahead and implement an example and see it in practice. So I'm going to create a new Python file here, and I'm going to call this Iterator. Right, now what I would like to do here is I would like to have a functionality, a couple of classes, a couple of iterators that will will traverse a collection of words and will return them either in an alphabetical order or in a reverse alphabetical order. Now, of course, you could do this very easily with functions on a collection. The point here is not to reinvent the wheel. It is to show you how you might implement that if you choose to do that for whatever reason, right? So class alphabetical order iterator. Okay, now let's define, or rather override, the init method and provide the words here as a collection, and then reverse of type Boolean. And by default, that's going to be false. Okay, so we're going to have self.collection is going to be equal to sorted of words. So we're going to sort the words in our collection, and then self.reverse is going to be reverse. Okay, and we're going to also store self.position is going to be length of words -1 if reverse else 0. So we're either going to start at 0 or at the last element. Okay, so let's implement the two methods. First, we're going to have next, and here we'll have value equals self.collection of self.position, and then self.position plus equals -1 if self.reverse else 1. So depending on which way we go, we either go back or we go forwards. Okay, and then we'll simply return value. Very simple. Now let's define has next. Okay, and here we can say if self.reverse and self.position greater than -1, return true. Elif not self.reverse and self.position smaller than length of self.collection. Okay, and in this case, return true, else return false. Okay, so we're just trying to see if there is any element that is after the current one. Right, so very simple, very intuitive. Now let's define a class words collection. And we're going to override the init method here with a collection. And we're going to say self.collection equals collection. And then we have def get iterator. And here we will return alphabetical order iterator with self and self.collection. Okay, so this is the alphabetical order. Now let's define get reverse iterator. And we will, of course, return the reverse one. So return alphabetical order iterator with self.collection. Sorry, we don't need to pass the self. I don't know why I put that here. Right, and same for here. Right, so self.collection, and then here we have true. Okay, so the reverse iterator is true. Right, so we have main, and here let's create our collection. So collection is going to be words collection of, let's have some words, John, Alice, we have Michael, and maybe Carol. Okay, so random order. Now, iterator is going to be collection dot get iterator, and reverse iterator is going to be collection dot get reverse iterator. Right, so let's print out some elements while iterator dot has next. Okay, in this case, we're just going to print iterator dot next, and let's print out a empty line here, and then we're going to say while reverse iterator dot has next, we're going to print the reverse iterator dot next. Okay, so now if I haven't made any mistakes, we should be able to see the result. Now here I need to provide a collection. That's my mistake. Now let's go ahead and run this again, and then we have our result. So the first one is going to be alphabetical order, and then for the second iterator is going to be reverse alphabetical order. So that is how you might implement an iterator in your own code. All right, in this video, we're going to talk about the mediator pattern. So the mediator pattern is very useful when we have multiple components in our system that kind of individually do their own thing, do their own processing, and then need to communicate with each other. Okay, so you can think about a distributed system where various nodes communicate with each other directly, right? So we want to have this kind of communication. Now, of course, in a system, when the nodes or the distributed components communicate directly with each other, it means that they have to know about each other, right? They have to know how to contact every other component that they need access to. So this is obviously a problem, especially when the system grows and when we have dozens, hundreds, thousands, or even millions of nodes, right? You can think about a chat application where we have millions of users that need to be able to communicate with each other. They need to know how to contact each other. In a chat application, for example, your phone doesn't talk directly to another phone. What it does is it talks to a central server, and then that server relays the message to the required destination. So this is the mediator pattern. You want to have a central location where each client communicates or sends their message to only one destination, and then that destination, based on that message, will forward it to the appropriate node. Okay, so that is the mediator pattern. It provides a central object that is used for communicating between objects. We've talked about chat applications, but also this can be used in larger applications with various components, or let's say microservices or things like that. Components that need to communicate with each other and share information should have a central location where those messages are being sent. The objects don't talk to each other, they talk to the mediator, and this obviously reduces dependencies between objects. The objects no longer need to know how to reach every other individual node in the system. They just know how to reach the mediator, and then the mediator will forward the message to the final destination, right? So very simple, very intuitive. Now let's implement a program to kind of see how this works in practice. So I'm going to go ahead and create a new Python file here called Mediator. And here we're going to have a very basic chat system, or rather group chat system, where each user can send a message to all other users, right? So we'll see how that works. Now, first of all, I need to import from future import annotations. Okay, I want to be able to call or reference classes before I define them. So here I have a chat user class. Okay, I'm going to have a mediator variable that's none by default. And let's initialize the element or override the init method and provide a name as a string, right? So self.name equals name. All right, so let's implement the method set underscore mediator. And here we have med mediator. Okay, which we haven't defined yet, but we will, no worries. Now, self.mediator is going to be mediator, or rather med, as I've defined it here. All right, now we need a send method, which will have a message of type string, and we're going to just print a f string that says self.name colon sending message MSG. Okay, so that is the send message, and we're going to say self.mediator.send underscore message, which is a function that we will define at some point, MSG and self. Okay, and finally, we need a def receive with self and MSG of type string. So this is where we receive the message, and we just want to print line an f string with self.name colon receiving message MSG. All right, so that is our chat user. Now let's go ahead and define a class mediator. And here we have a list of users, an empty array by default. And we're going to have def add user with user of type chat user. Okay, so here we just want to add self.users.append with user, and we want to set the mediator for this user as well. So user.setMediator with self. Okay, so that is our add user, but we want to have a send message method, def send message. And here we want to have a MSG of type string. And we want the user that sent that message, chat user. Okay, for u in self.users, here we can say if u is different from user. We don't want to send the same message to our own user, to the user that sent it initially. We say u.receive, and here we have MSG. Okay, so we're just calling the receive method on each user that we have in our list. Right, so that's all we need. Now let's go ahead and create our structure. So mediator is going to be a mediator instance. And let's create maybe 3 users. Alice equals chat user with the name Alice. Then we have Bob chat user with the name Bob. And then finally, let's add Carol is a chat user with the name Carol. Right, so we have our users. Now let's say mediator.addUser Alice and duplicate that twice. I'm going to add Bob and I'm going to add Carol. All right, so we have our structure. Now any one of these users can send a message. So I'm going to say carol.send hi everyone. Right, so let's see how that works. Let me just run this. And we get Carol is sending the message, hi everyone. And then Alice is receiving that message and Bob is also receiving that message. So we can see that we have this mediator pattern where we have the central structure, which is used to facilitate transmitting messages between our components, in our case, multiple chat users. In this video, we're going to talk about the Memento design pattern. And to kind of quickly give you an idea of what this is about, think of a undo or redo system where you have, let's say, an editor and you want to store a trace of states that you went through and operations that you did so that you can undo any operation that the user has done, whether it's writing something or deleting or, whatever keyboard shortcut they might use. You want to encapsulate that so that you can have this chain of events that you can kind of go back and forth into. So this is a memento. We have some operations that the user does. For example, here we have multiple text edits, and we encapsulate those with their own state into some quote unquote mementos, right? And then we can kind of move back and forth between this chain of operations. This will allow us to do an undo or redo and go back and forth. So the memento at its core is simply a system to save and restore previous state without revealing the implementation details. So we don't care what the user actually did or what the details are in each memento. We simply want to be able to move back and forth between the chain, between elements of this memento chain. We have three main components. First of all, we have the memento, which stores the state, which is kind of the implementation or the details of what has been done. We have the originator, which creates the state, and we have the caretaker, which decides to save or restore the state. So the caretaker will allow us to move forwards or backwards in the chain. Now, usually in these kind of systems, you have undo, which goes back one element in the chain, and redo, which goes forward. But there's really no reason to limit ourselves to one step. We can actually jump through the chain as much as we like, as long as we have the ID of the element of the memento that we want to get to. All right, so let's go ahead and implement this in code to see how this might work. So I'm going to go ahead and create a new file here called Memento. Now here we're going to define, first of all, we want to use data classes. So we're going to say from data classes, import data class. And we're going to create an @data class. And we're going to call this Memento. And we're going to just store one attribute, which is state, and we're going to make that a string. So let's define an originator. This is, remember, this is the one that creates the state for us, creates the mementos. And let's override the init method where we pass a state, and we're going to store it, self.state equals state. Okay, so we have that. Now let's go ahead and create a function called createMemento. And here we will simply return memento of state, self.state. Okay, and then we have restore memento. And here we have memento of type memento. And here we just say self.state equals memento.state. Okay, so here is where we keep the current state of the system. And then we're going to define a class caretaker. Okay, here we will have a memento list. Okay, or you could call this mementos with an S at the end. It doesn't really matter. Let's define a save underscore state function where the state is of type memento. Okay, self.memento list.append, we're going to add the state. Right, so we have our state, or rather our memento in our memento list, and we're going to define restore self and index of type int. And here we just return memento list, self.memento list of index. Right, so that is all that we need. You can see the actual implementation is quite simple. Let's go to our main. And here, what I would like to do is I would like to create a few states. We will add them to our list, and then we will move back and forth between the states. So first of all, we're going to have an originator. That's going to be originator of, we're going to call this initial state. Okay, and a caretaker, that's going to be an instance of caretaker. All right, so we're going to say caretaker.saveState, and here we're going to have originator.createMemento. Okay, so we have saved our first state in our caretaker. Let's print a message, and here I'm going to have an F string. Current state is originator.state. Right, so this is my original state. So now let's update this. So originator.state is going to be state 1, let's call this. And then we're going to say caretaker.saveState originator.createMemento. And then I would like to print the current state again. So let me just copy this and paste it here. So we are now at state 2. Let's create another one. So we have another state, copy and paste that, state 2, originator.createMemento, that's fine. And then current state is, that's fine. Right, so we now have 3 states, so we can actually move between them as much as we like. So we can say originator.restore memento. So here we can provide the required memento, and we're going to say caretaker.restore, and we need to provide the index. Let's go up 1, so from state 2 to state 1, right? So that is going to be 1, and we're going to print the current state. Okay, so copy and paste that. So we have moved to the first state, or rather we have state 0, state 1, and state 2. Okay, we have moved to state 1, but let's move to the state 0, quote unquote. So we can say originator.restore and caretaker.restore 0. Okay, and we're going to print the current state, and then we can actually jump to the last state, right? We don't need to go step by step. We can just jump between them. So we can say originator.restore memento, caretaker.restore to 2, and we can print the current state. Right, so that is all there is to it. We kind of jump around between the states that we have. Let's go ahead and run the code. So what do we get? We get the current state is initial state. Then we move to state 1. Then we move to state 2. We go back 1, right? So we go to state 1. We go back to 0. So we have initial state. And then we kind of jump straight to state 2, bypassing state 1. So current state is 2. Okay, so you can imagine a system where these states are dynamically generated based on user actions, and the system will kind of go back and forth. Of course, a real-world system like an editor would go back 1 or forwards 1, but as you can see, we can jump around if we need to. So that is the implementation of the Memento pattern. In this video, we will talk about the observer design pattern, and this design pattern is one of the most useful ones and one of the most common ones. So you will see it quite often in various projects and in a lot of code, in a lot of components in the code. So what it does at its most basic is, let's imagine we have 2 components. One is kind of a time-intensive processing unit that does some processing in the background and at some point will return a result. And we have on the right side, we have a user of that result. Now, this is not an actual user. It's not an actual person, more of a component in the application, right? So here, the user requires this result, so it's waiting for it. And it has basically 2 options. One option, kind of the naive implementation, would be to periodically poll this time-intensive processing unit just to ask for the result. And as it's shown here, you ask it once, it says no. Is it ready yet? No, not yet. Is it ready? No. Is it ready? No. So you can ask many, many times. You will get the result no until eventually you will get the yes. So of course, this would lead to a lot of communication back and forth and a lot of wasted kind of processing, right? And this problem would get exponentially worse when we have multiple of these users. So if everybody starts to poll at the same time, if we have dozens or hundreds of these users, then that could cause a major issue where we cannot deal with that amount of communication, right? So we need to find a better solution. Obviously, the solution would be to implement some sort of middle layer here that groups together this communication so that we don't have to poll it many, many times. So we implement some sort of registry here that is simply kind of waiting for the time-intensive processing unit to finish and return the result. So as soon as the result is returned, we can start to notify the intended users. So the way this works is the users basically register their interest to this result. And as soon as that becomes available, then they will get notified. We can also have in this kind of architecture, we can also have multiple types of results that can become available. So the users or the interested components would register their interest for specific results or for specific types of results, and then they only get notified when those results come in. So to kind of sum up the observer pattern, it defines a subscription mechanism, similarly to how you might subscribe to a newsletter online, or you might purchase a subscription to your favorite newspaper in real life and get it delivered to your home. This is a very similar mechanism where users subscribe for events that they're interested in. We can notify multiple objects simultaneously. So whenever some result is available, then multiple interested parties get notified. And also we can have multiple types of events notifying multiple objects. So there's kind of a one-to-many relationship where we have multiple interested parties to one object, right? One type of response. Of course, we can have multiple types of responses, but each individual type of response can have multiple interested parties. So to kind of sum up in a bit more pseudocode kind of architecture, we have here an event generator and we have the event manager. The event manager gets notified when the events are available, and it stores a list of subscribers, right? The list of subscribers can be updated whenever a new subscriber comes in or a subscriber leaves. And then when the event becomes available, then we notify the subscribers. We have a standard subscriber interface that is implemented by whoever is interested in that event. And then they have an implementation, a method that gets called when the event becomes available. Right, so that is the theoretical introduction. Let's go to code and have a look at how we can implement this. So here I will create a new file, and I'm going to call this observer. Right, so first thing, I'm going to import from ABC, import ABC and abstract method. Okay, so that we can create some abstract classes. So the first one is going to be event listener that inherits from ABC, and we'll define an abstract method called def update. And here we have an event type of type string, and let's say a file. Okay, we want to notify when that file becomes available. And for now, we have pass. Now we have a class event manager. Okay, and here I don't need these parentheses. We can override the init method, and we can add a operations list. Operations, and here we can store it self.operations equals operations. All right. Now we can also have a self.listeners that is a dictionary by default. And we're going to say for op in operations, we instantiate those listeners. So self.listeners of op, of operation, equals a list. So for each operation, we have a list of listeners. Okay, it's empty for now. Right, so let's define a subscribe method where we have an event type of type string, and we have a listener, which is going to be an event listener. So this is very simple. We just say users equals self.listeners of event type. Okay, and we just add our user to these users, or our listener to these users. So users.append, and here we have our listener. Right, so this is the subscribe. Now we need the opposite, def unsubscribe. And here we just need the, actually we need both. We need the event type of type string, and we need a listener of event listener. Okay, so very similar to what we've done here. I'm just going to copy this, paste it. So we retrieve the users of the event type, and we, instead of append, we will use remove. Remove the listener. All right, so that is the users or subscribers list. And then we need a notify method of event type and a file. Okay, so here we simply retrieve the event type. So users equals self.listeners of event type. And then we want to notify or update those users. So we're going to say u.update of event type and file. And here we have for u in users. All right, so we just notify all these interested parties. Now, we're going to have an editor class that generates our events. So editor events equals event manager of, and we have, let's add two types of operations. We have an open and we have a save. We can of course have as many as we want, but we're just going to limit to these two. And then file equals none by default. So let's define an open file method, which has a file. And here we can say self.file equals file. And then let's print a message, an F string saying something like editor opening file, and we can print out the file here. All right, so we open the file. So of course we need to notify everyone of this event. So self.events.notify. Okay, and here we can notify of the event open and the file. All right, so that is the open file functionality. We can also have a save file, so def save file of self and the file that we want to save. And this is going to be quite similar. We're going to say print. We don't need to save the file because first we assume it's open before we save it. So we already have the file stored, and we can say print editor. Instead of opening file, we'll say save or saving file, and let's print the file here. All right, and then we can notify the event. So self.events.notify, and here we have save and file. Right, so that is our editor. It simply allows us to generate events and call the manager to update everyone interested. Now let's define some listeners. So of course, we need to implement the event listener abstract class, right? So here we will have two listeners. First one is going to be an email listener that will kind of send emails whenever an event has occurred. And the second one will be a logger that will basically log events. So the first one, class email notification listener. This will implement event listener. And we need to, first of all, let's define or override our init and pass here the email that we will quote unquote update or send emails to. So self.email equals email. Okay, and then we need to implement the update method that we have defined here. So def update. Okay, we have our file. So here we can simply print a message to kind of simulate sending that email. And we can say email to self.email. And we can say let me just, there we go. We can say someone has performed event type operation on the file. And that's pretty much it. We can just simulate sending that email. We don't need to actually implement that functionality. So that is one listener. Let's define another one. Let's say log open listener. That's going to be an event listener. Here again, we need to override our init method. And we have log file, self.log file equals log file. Okay, and we need to override our update, or rather implement our update method. And here we can say something similar. So print an f string, save to log self.log file, colon, someone has performed event type operation on the file. All right, so that is our listener. Those are our two listeners. So all that's left to do is put this together in our main function. So main, we have our editor equals editor. Okay, instance of that editor. Let's instantiate our listener. So email listener equals email notification listener. And here we need to pass an email. So let's say test@gmail.com. And then we have our log listener. That's going to be a log open listener. And here we have, let's say, path to log file dot text. Okay, so we have our two listeners. So let's go ahead and start to subscribe to events. So we can say editor.events.subscribe. And we want to subscribe to open events with the log listener, but we also want to subscribe to save events. So editor.events.subscribe to save events log listener. So we want to log everything. However, for the email, we only want to email when we have a save, let's say. So editor.events.subscribe, save, and email listener. All right, now editor, let's generate some events.open file, and here test.text, and editor.save file. Okay, why do we need a file here? We don't really. Let me update this. We don't actually need to save the file, to pass the file here because we already have it. So self.file and notify self.file. All right, so that is looking good. I think that's pretty much it. Let's go ahead and run the code. There we go. So no problems. Editor has opened the file, and then we can see that immediately the log log listener has printed out a message, someone has performed an open operation, and then as soon as we save the file, both listeners will print out a message, or rather get notified, right? So someone has performed the save, someone has performed the save. The first one is for the logger, and second one is for the emailer. So this is how it works. Whenever we generate an event, the event manager will notify every subscriber, right? So we can subscribe or unsubscribe to various events. All right, in this video, we're going to talk about the state design pattern. So the state is basically thinking of your code or your program as a state machine, or in our case, a state algorithm. That simply means that your algorithm can only be in a certain number of predefined states and cannot kind of deviate from those, right? So we have this example here of a let's say a article on a blog post or on a news site, and it can go through, let's say, three steps or three states. The first one is going to be draft, where the author just creates the article. Then it moves into moderation, where the let's say someone else would come in and check the article to make sure it's fit for production. And then it will get published, right? Now, from moderation, it can go back to draft. So we can move back in the kind of stack of states, but it can also go forward. So here we have the option. However, there are some states that cannot move between them. So for example, it cannot go from published to moderation. It has to go from published to draft and then to moderation, right? So there are some limitations in how you can move through this tree or through this chain of states. You can go from some to others, but not from certain ones to other ones. Importantly, also, the state itself is encapsulated in an object that we can pass around in our code as we need to. So the object, an object changes its behavior based on an internal state. So depending on which state we are on, we can update our code when we receive that state object. So this is encapsulated in an object. It gets passed to some component, and that component updates its internal logic based on the state it receives. At any moment, there's a finite number of states a program can be in. So as we've seen here, we have only 3 in our example. Of course, you will define as many as you require in your code. And then state can be encapsulated in an object, as we discussed. All right, so that's it for the quick introduction. Let's move to code and see how we implement this in practice. Right, so let me just create a new file here called state. Now, the implementation for this design pattern is logically quite simple, but we do have quite a bit of code to get through to implement this, to implement the state in our code. So what I would like us to think of is a game that has, let's say, 4 states that it can be in. So first of all, we have the kind of welcome screen where we open up the game and are ready to start playing. We have the playing state where the user or the player is actually engaged with the gameplay. Then we have the kind of pause or break state where we take a pause. And then we finally we have the end game state where the game has finished and we can kind of go back and restart the game. So we have the option to go back and forth through these states. So let's implement this in our code. All right, so the first thing we need is from future import annotations. Okay, we will need to use some classes before we define them. We will also need to import random, and then from ABC import ABC and abstract method. Okay, so we can define some abstract classes. Now, the first thing we need to do is we need to define a game class, and let's override the init method. And here we need to we don't need to provide any arguments, but we need to store self.state. And by default, at the beginning of the game, we will have what we call an welcome screen state. We haven't defined this yet, but we will shortly, right? For the welcome screen state, we will need to define the abstract class. So we will need to take a bit of time before we actually implement that. Right. So we also want a function called change state, where we pass the state object here and we update our internal one. Okay, self.state equals state. So that's all for our game. Now let's go ahead and define the abstract class for the actual state object. So class state of ABC. Here we have def init. We're going to override the init method and we need to pass a game to this method, and we're going to store it here. Self.game equals game. And let's print out a message to see which state we are on. So we have an F string currently in self state. Right, so now we need to define our 4 methods that relate to our 4 states we have in our code. So first of all, abstract method, we have def on welcome screen. Okay, and we don't need any parameters and we're just going to pass for now. We have a second one, def on playing self, and we're going to pass. We have an abstract method, def on, this is going to be on break. Okay, when we actually take a break from the game. And then the final one, abstract method. Here we have def on end game. Okay, and pass. Right, so we have our state. So now we need to implement the 4 classes. So the first one is going to be welcome screen state. This is going to be a state. Okay, and we need to implement all these 4 abstract methods. Okay, so I'm going to implement abstract methods, select all of them, and implement them here. Now, before we actually add functionality to these methods, we will need to have all the other states as well. So it might be easier to just put up this structure for all the states. So let's add class playing state that inherits from state, and this will also implement all the abstract methods. Okay, so we have welcome screen, we have playing state, we will need the class break state. Okay, let's implement the abstract methods. And then after that, we will go through each one and implement them correctly. And then class, the final one is going to be end game state, which also is a state. And we need to implement all the abstract methods. Right, so we have all this. So we have to go through each one and implement them step by step. So not here. The first one is going to be welcome screen state. So welcome screen state, we cannot move from welcome screen state to another welcome screen state. However, we can just simply print out a message saying currently on welcome screen. Okay, now we can move from welcome screen state to playing. So here we can say self.game.change state, and we need to pass a playing state with self.game. Okay, so we move to that. Now from welcome to break, we cannot move, right? So here we're just going to print a message from welcome to break not allowed. Okay, and then from welcome to end game, again, not allowed. From welcome to end game, not allowed. All right, so that is our welcome screen state. Now let's move to playing. So from playing to welcome screen, again, it's we cannot move, so not allowed. From playing to welcome, not allowed. Here on playing, we are already here, so we're going to print a message, currently playing. For the break, from playing to break, yes, we are allowed to do that. So self.game.change state, we move to break state with self.game, and then from playing to game to end game, not allowed. So print, actually from playing to end game, we are allowed to do that. So self.game.changeState end game state, self.game. We can finish the game at some point. All right, break. From break to welcome, we are not allowed. So print from break to welcome, not allowed. From break to playing, yes, of course, we can do that. So self.game.changeState, playing state. Now, obviously, in a real-world situation, you would not create a new playing state. You would retrieve the existing one, but we're going to simplify our code here just to kind of work on the design pattern. Now, from break, we are already on break. So let's print that here, currently on break. And then from break to end game, we are not allowed. From break, we can only go back to playing. So here we can say print from break to playing to end game not allowed. All right, and the final one is the end game state. So from end game to welcome, yes, we can go there. So game.changeState welcome state with self.game. From end game to playing, no, we cannot do that. So print from end game to playing not allowed. Okay, from end game to break, we cannot do that. So from end game to break not allowed. And then finally print from or currently on end game. All right, wow, that's quite a lot of print messages, but we got through it. So now all that's left for us to do is implement the main. Okay, so here we will instantiate a game, and I want to introduce some randomness, some random moves from one state to another. Okay, so I'm going to say for I in range of, let's say we're going to do 20 moves, and we're going to say state equals random dot rand range of 4. Okay, we have 4 states. We're going to introduce 4 possibilities. So if state is 0, then we can say print move to welcome. And here we can say game.state.on welcome screen. Okay, so we're trying to move to welcome. We might be able to, we might not, depending on which state we are currently on. Elif state equals 1, then in this case we move to playing. Okay, and we have game.state.on playing. Elif state equals 2, then we want to move to break. Okay, and we're going to say game.state.on break. Okay, and else we are at the final step, so we can say print move to end game. Okay, and game.state.on end game. All right, so that's pretty much it. If I haven't made any mistake, I did type more than 100 lines, so let's go ahead and try it out. All right, so it's working fine. So let's have a look at what it's doing. So we start off in welcome screen state, then move to end game. Well, we are not allowed. We're trying to move to break. We're not allowed. End game, welcome. We're currently on welcome. Break, not allowed. Playing, that's fine. We can move to playing. From playing, we try to move to playing about 3 times, not allowed. But then we try to move to break, right? So we can do that. So it kind of goes on like this for a while. It sometimes manages to move to a state that's allowed. Most of the times it would probably not do that, right? But we can see how we can move from one state to another in our game. This is how we implement a state design pattern. Of course, it will be a bit more complex in a real-world situation, a real-world system, where you need to store a lot more information in your state so that you can pass it around and your components will update based on that. But the concept of a state machine is very similar to what we did here.